On the 12th of July, 1969, a human being stood on the surface of another world for the first time. The surface was gray and powdery and utterly still, no wind, no weather, no sound that did not come from the suit or the equipment or the voice in the earpiece. The sky above was black, not the deep blue of Earth at altitude but an absolute, lightless black, because there was no atmosphere to scatter sunlight into color. The horizon was close, the curve of the small world bending the surface away with a sharpness that felt wrong to a brain evolved for the vast flat plains of an African savanna. And yet it was real. The footprints were real. The dust that rose in perfect parabolic arcs when the boot pressed down and settled instantly, no air to keep it suspended, was real. 12 human beings walked on the moon between 1969 and 1972. Then we stopped going. For more than 50 years, no human being has stood on any surface other than Earth. The robotic explorers we have sent, the Mars rovers, the lunar orbiters, the probes that have visited every planet in the solar system and passed beyond it into interstellar space, have returned data and images of extraordinary scientific value. But no human hand has touched the soil of another world since Harrison Schmitt picked up a piece of orange glass from the Taurus Littrow Valley on the 14th of December, 1972, climbed back into the lunar module, and left. The orange glass is still there, in the valley he found it in the airless dark of a lunar night that lasts for 14 Earth days. It has been waiting for 50 years. It may be waiting still. We are going back. Not as a final act of nostalgia for the brief, extraordinary moment of Apollo, but as the beginning of something different. Something permanent. The Artemis program, named for the twin sister of Apollo in Greek mythology, is not designed to plant flags and collect samples and return home. It is designed to stay. To build. To establish, on the surface of the Moon and eventually on the surface of Mars, the first permanent human presence beyond Earth. The first outposts. The first steps in a process that, if it proceeds as its architects intend, will eventually lead to humans living and working and perhaps being born and growing old on worlds other than the one where our species began. Tonight we follow that story, from the moon landing of the past to the Mars outpost of the future, from the engineering of rockets and habitats and life support systems to the biology of the human body in space, from the ice at the lunar South Pole to the ancient riverbeds of Mars. Find a comfortable position. Let the weight of the world you are lying on settle beneath you. Somewhere above the atmosphere, the moon is rising, its surface gray and patient and unchanged since the last human footprint was pressed into it half a century ago. We are going back. And this time, we are staying. You chose to spend this night thinking about other worlds. There is something specific about that choice, something that distinguishes the person who finds comfort in the scale of the cosmos from the person who finds it overwhelming. The idea of humans on Mars, of outposts on the moon, of civilization extending beyond the single planet where it began, for some people, that idea produces anxiety, a sense of the familiar world becoming unstable. For others, and you are apparently among them, it produces a quiet sense of rightness. Of course we go. Of course we explore. Of course the story continues beyond the boundary that has contained it so far. The universe is too large, and we are too curious, and the next world is too close, to stay only here. Wherever you are watching from tonight, Whatever corner of the one world we currently inhabit, you are watching from a planet with a sky above it that is full of destinations. The moon is there whether you can see it or not. Mars is there, a small red point of light that has been watched by human eyes for as long as there have been human eyes to watch. The planets and the stars beyond them are there. And the fact that we have spent more than 50 years since Apollo without returning to any of them is not the end of the story. It is the middle, the long pause before the next chapter. The next chapter is beginning. I'm glad you're here for it. Leave a comment with where you're watching from tonight. Knowing which corner of Earth is looking up always means something to me. If this kind of journey into the future of human space exploration, into the science and engineering and human story of what it means to build a life beyond Earth, is the kind of thing you want to return to, consider subscribing. We go somewhere new every few weeks. The only requirement is a willingness to look up. The Apollo program was, by any reasonable measure, the most audacious engineering achievement in human history. Between 1961, when President Kennedy committed the United States to landing a man on the moon before the end of the decade, and 1972, when Apollo 17 lifted off from the lunar surface for the last time, approximately 400,000 engineers, scientists, technicians, and support workers, the vast majority of them based in the United States, built the infrastructure, the spacecraft, the rockets, the tracking systems, and the procedures required to send 12 human beings to another world and return them safely. The program cost, in today's dollars, approximately $280 billion. It succeeded in every crewed mission after the tragedy of Apollo 1, in which 3 astronauts died in a launchpad fire during a test. It produced 6 successful moon landings, approximately 842 pounds of lunar rock and soil samples, an enormous body of scientific data, and a set of photographs, Earthrise, the whole Earth from Apollo 17, the boot print in the gray dust, that changed how the human species perceived itself. And then it stopped. The reasons for the end of Apollo are complex and contested, but they reduce roughly to 2 factors: cost and motivation. The Apollo program was driven primarily by the geopolitical competition of the Cold War, the specific need to demonstrate American technological and ideological superiority over the Soviet Union in the most visible possible arena. Once that demonstration had been made, repeatedly, the political will to sustain the enormous expense of continued lunar missions eroded quickly. The Nixon administration, facing domestic political pressures from the Vietnam War, inflation, and social upheaval, cut NASA's budget dramatically in the early 1970s. Apollo 17's crew left the moon in December 1972, and the 3 subsequent Apollo missions, 18, 19, and 20, were canceled. The hardware was repurposed for Skylab and the Apollo-Soyuz test project. The infrastructure was mothballed. The engineers who had built the Saturn V rocket retired or moved to other programs. The specialized knowledge of how to return humans to the moon dispersed. The window closed. The 50-year pause that followed was not a complete absence of human spaceflight. The Space Shuttle program flew 135 missions between 1981 and 2011, delivering satellites, conducting science experiments, and building the International Space Station, a permanent human presence in low Earth orbit, approximately 400 kilometers above the surface, which has been continuously inhabited since November 2000. The ISS is, by any measure, a remarkable achievement, a structure assembled in orbit over more than a decade, housing rotating crews of 6 astronauts from multiple countries, conducting science in the microgravity environment that is impossible to replicate on Earth. But it is not deep space. It is not another world. It is, from the perspective of genuine interplanetary exploration, a very sophisticated frontier post at the very edge of Earth's backyard. The new space age that began in the 20-teens and accelerated through the early 2020s is different from the Apollo era in several fundamental ways. The most visible difference is the role of commercial companies. SpaceX, founded by Elon Musk in 2002 with the explicit goal of making humanity multi-planetary, has developed the Falcon 9 rocket, the first orbital rocket to routinely land and reuse its first stage, and the Falcon Heavy, and is developing Starship, a fully reusable super heavy launch vehicle designed to carry large payloads and crews to the Moon and Mars. Blue Origin, founded by Jeff Bezos, is developing the New Glenn rocket and the Blue Moon lunar lander. Rocket Lab, Sierra Space, Axiom Space, and dozens of other companies are building launch vehicles, habitats, life support systems, and space stations. The commercial sector is now the primary driver of launch cost reduction and hardware development, with NASA increasingly functioning as a customer and systems integrator rather than the sole developer of all hardware. The second fundamental difference is the international character of the new effort. The Artemis Accords, a set of bilateral agreements on the principles governing civil space exploration, initiated by the United States in 2020, have been signed by more than 40 countries as of the mid-2020s. The European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and numerous other national agencies are contributing hardware, personnel, and expertise to the Artemis program. The International Space Station Partnership, which included Russia alongside the Western partners, demonstrated that international space cooperation was possible even during periods of geopolitical tension. The Artemis program is building on that precedent, though the geopolitical landscape of the 2020s has complicated the calculus, and China's independent lunar exploration program, which aims to land Chinese astronauts on the Moon by the late 2020s, has introduced a competitive dimension reminiscent, in some ways, of the Cold War space race. The scientific motivation for returning to the Moon is also substantially richer than it was during Apollo. The Apollo missions visited 6 sites, all near the lunar equator, all chosen primarily for landing safety rather than scientific interest. The lunar South Pole, which post-Apollo orbital observations and the deliberate impact of the Lacrosse spacecraft in 2009 have confirmed harbors significant deposits of water ice in permanently shadowed craters, was not visited. The far side of the Moon, which never faces Earth, was not visited. The volcanic regions, the large impact basins, the ancient highland terrains that record the earliest history of the solar system, most of these were either not visited or only briefly sampled. The Moon is a 4.5 billion year geological archive of the early solar system, and Apollo barely scratched its surface. The motivation that is perhaps most honestly acknowledged in the planning documents of the new space age is not scientific, not commercial, and not geopolitical, it is existential. The recognition, articulated with increasing frequency by space agencies, commercial companies, and scientists, that the long-term survival of the human species may depend on its becoming multi-planetary. Earth is a single point of failure for the entire human project. A large asteroid impact, a supervolcanic eruption, a pandemic more lethal than any in history, a nuclear war, a runaway climate perturbation, any of these could, in a worst case, end human civilization or the species itself. The probability of any single catastrophe on any given century is low. Over timescales of millions of years, the probability that Earth remains indefinitely hospitable to human civilization approaches zero. The insurance argument for a multi-planetary species is not paranoia. It is a straightforward reading of the geological and astronomical record. We are going back to the moon not because of what the moon is, but because of what it represents, the first step in a trajectory that does not end at the lunar surface. The moon is a proving ground, a construction site, a laboratory for developing the technologies and the operational experience needed for Mars. Every system tested on the moon, the habitats, the life support, the resource extraction, the communication and navigation infrastructure, the human physiological adaptation to reduced gravity, reduces the risk of the Mars missions that follow. The moon is close enough that a rescue mission is conceivable within days. Mars is not. The moon is where we learn how to make mistakes without dying from them. Mars is where we apply what we learned. The 50-year gap between Apollo and Artemis has also produced something Apollo lacked, a generation of people for whom space exploration is not a Cold War competition but a genuine scientific and civilizational project. The astronauts of Apollo were almost exclusively military test pilots, selected for their performance in high-stress aeronautical environments. The astronaut corps of the 21st century includes geologists, biologists, physicians, engineers, and physicists, people selected as much for their scientific expertise as for their piloting skills, because the missions they will conduct on the lunar surface and eventually on Mars require genuine scientific training rather than primarily flying skill. The science of the new lunar program will be deeper, broader, and more systematic than Apollo's science, precisely because the people conducting it have been trained to do science rather than primarily to survive in extreme environments. There is also a cultural dimension to the return that is worth acknowledging. The Earthrise photograph taken by Apollo 8 astronaut William Anders on Christmas Eve 1968, the first image of Earth as a whole, a blue sphere hanging in the black of space above the gray lunar surface, is credited by many environmental historians with catalyzing the modern environmental movement. Seeing Earth from outside, as a single fragile object with no visible political boundaries, changed how many people thought about the planet and its resources. The images that future Artemis and Mars astronauts will take, of Earth from the lunar surface, of Earth receding to a bright dot during the months-long Mars transit, will produce their own cultural resonances, their own shifts in collective human self-understanding. We cannot know in advance what those shifts will be. But the history of human exploration suggests they will be profound. The architecture of the Artemis program is a layered system of rockets, spacecraft, orbital stations, and surface vehicles designed to accomplish what Apollo could not just a visit, but the beginning of a sustained human presence on and around the moon. Understanding the architecture requires understanding what makes deep space travel fundamentally different from the low Earth orbit missions that have dominated human spaceflight for the past 5 decades, and what makes each component of the Artemis system a necessary part of the whole. The Space Launch System, SLS, is NASA's heavy-lift rocket, designed to carry the Orion spacecraft and its crew from Earth to lunar orbit. The SLS Block 1 configuration, which flew on the Artemis I uncrewed test mission in November 2022, stands 98 meters tall and generates approximately 8.8 million pounds of thrust at liftoff, comparable to the Saturn V of the Apollo era, making it one of the most powerful rockets ever flown. The core stage burns liquid hydrogen and liquid oxygen in 4 RS-25 engines inherited from the Space Shuttle program, augmented by 2 solid rocket boosters derived from Space Shuttle heritage hardware. The Artemis I mission flew the Orion capsule on a 25-day uncrewed test around the Moon and back, validating the spacecraft's heat shield and the high-speed re-entry from lunar return trajectory, a re-entry at approximately 39,000 kilometers per hour that subjects the heat shield to temperatures approaching 2,700 degrees Celsius. The Orion spacecraft is the crew vehicle, the capsule in which astronauts will live during the journey to and from the Moon. It consists of a crew module, capable of supporting 4 astronauts for up to 21 days, and a service module, provided by the European Space Agency, which supplies propulsion, power, thermal control, and consumables. Orion is substantially more capable than the Apollo command module. Its crew module is 50% larger by volume, and its service module carries significantly more propellant, allowing it to perform the orbital insertion and departure maneuvers needed for lunar orbit operations. The life support systems are more sophisticated, the avionics are more advanced, and the abort system, a tower of solid rockets at the tip of the spacecraft capable of pulling the crew module away from an exploding launch vehicle in fractions of a second, has been tested to full performance. The Lunar Gateway is the orbital element that distinguishes Artemis from Apollo most fundamentally. Rather than traveling directly from Earth to the lunar surface and back, as the Apollo missions did, the Artemis architecture uses a small space station in a near rectilinear halo orbit around the Moon as a staging point. The Gateway will be assembled incrementally from modules contributed by NASA and international partners, the power and propulsion element, which provides electrical power, and the solar electric propulsion system that allows the Gateway to reposition its orbit, the habitation and logistics outpost, which provides crew quarters, life support, and storage, modules contributed by the European Space Agency, the Japan Aerospace Exploration Agency, and others. The Gateway is not permanently crewed. It will be occupied during Artemis missions and will otherwise operate autonomously, but it serves as a logistics depot, a communication relay, a science platform, and critically, a waypoint from which lunar landers can depart for the surface and return without requiring the main Orion spacecraft to descend into the Moon's gravity well. The Human Landing System, HLS, is the spacecraft that will actually take Artemis astronauts from the Gateway to the lunar surface and back. NASA selected SpaceX's Starship as the initial HLS provider, a decision that represented a dramatic departure from traditional NASA procurement and generated significant controversy. Starship is a fully stainless steel vehicle standing 50 meters tall in its lunar configuration, capable of carrying large crews and substantial cargo to the lunar surface. It differs from all previous lunar landers in its scale, where the Apollo lunar module was a compact, purpose-built vehicle optimized for minimal mass. Starship HLS is large enough to serve as a habitat as well as a lander, with space for multiple crew members and significant pressurized volume. The choice of Starship as HLS means that the Artemis surface missions will have access to substantially more interior space and cargo capacity than Apollo, but it also means that the schedule and technical challenges of Starship development are directly on the critical path for crewed Artemis surface missions. The Artemis Astronaut Corps represents one of the most significant symbolic and practical changes from Apollo. The Artemis program has committed explicitly to landing the first woman and the first person of color on the Moon. The Artemis 3 mission, which will be the first Artemis mission to land astronauts on the lunar surface, will include a female crew member among the lunar surface crew, making her the 13th human to walk on the Moon and the first woman in history to do so. The broader Artemis astronaut class includes astronauts from NASA's international partners, and the program's long-term planning envisions international astronauts conducting lunar surface activities as the program matures. The extravehicular activity suits, the spacesuits worn outside the spacecraft on the lunar surface, have been redesigned from the ground up for the Artemis program. The Exploration Extravehicular Mobility Unit, or XEMU, and its successor the Axiom Extravehicular Mobility Unit, AXIMU, are designed to address the significant limitations of the suits used on Apollo and on the International Space Station. The Apollo suits were extraordinarily stiff at the hip and knee joints, making walking and bending difficult and fatiguing. The new suits incorporate advanced bearing systems at the shoulder, hip, and knee that allow a much greater range of motion, enabling astronauts to kneel, bend, and conduct the complex manual tasks required for geological sampling and equipment deployment on the surface. The suits are also designed to be sized for the full range of human body dimensions, male and female, different heights and builds, where the Apollo suits were built for a relatively narrow range of body types that excluded most women. The Artemis program has progressed through its early milestones with a combination of technical achievement and schedule delay that is characteristic of programs at the frontier of human capability. Artemis I flew successfully in late 2022. Artemis II, the first crewed mission, which will take 4 astronauts around the Moon without landing, is planned for the mid-2020s. Artemis 3, the first landing, follows. The schedule has been revised repeatedly as the complexity of developing Starship HLS, the gateway modules, and the new spacesuits has encountered the inevitable delays of frontier engineering. But the hardware exists, the program has funding and international commitment, and the trajectory is clear. The return to the Moon is not a plan. It is an ongoing engineering program with flight hardware on the launch pad. The Canadian Space Agency's contribution to the Artemis program illustrates the depth of international integration. Canada is providing Canadarm3, an advanced robotic arm system for the lunar gateway that will be capable of autonomous operation, maintaining and servicing the station without constant human supervision. In exchange for this contribution, Canada receives a seat on an early Artemis crewed lunar mission, making Canadian astronaut Jeremy Hansen part of the Artemis II crew, the first Canadian to travel beyond low Earth orbit. This exchange model, hardware contributions in return for crew access, is the same model that built the International Space Station partnership and is now being extended to the lunar program. It distributes the cost and complexity of the program while distributing the benefits of participation, creating a political constituency for continued support across multiple countries. The breadth of hardware under development for Artemis also includes a range of surface mobility systems. NASA and its commercial partners are developing lunar terrain vehicles, pressurized rovers capable of carrying astronauts tens of kilometers from the landing site across the lunar surface over multiple days, allowing exploration of the broader South Polar region rather than just the immediate vicinity of the lander. A pressurized rover fundamentally changes the scale of lunar surface exploration, rather than the short traverses of Apollo, limited by the unsuited astronaut's ability to walk and work in a bulky spacesuit for a few hours. A pressurized rover allows geologists to conduct regional scale surveys, collecting samples from multiple locations across a landscape and returning to the base habitat to sleep and eat in shirt sleeves before heading out again the next day. The lunar South Pole, with its complex terrain of crater rims and ejecta blankets and permanently shadowed regions, demands exactly this kind of mobile, multi-day exploration strategy. The 6 Apollo landing sites share a common characteristic: they are all within a few degrees of the lunar equator, in terrain that receives regular sunlight and where the landing approach geometry and communication geometry with Earth were manageable with 1960s technology. They were chosen for engineering reasons, not geological ones. The scientifically and practically most interesting region of the Moon, the South Pole, was not visited by any Apollo mission, and was not fully understood until decades of orbital observations changed the picture of what the lunar South Pole actually contains. The Moon has an axial tilt of only about 1.5 degrees relative to the ecliptic, far less than Earth's 23.5 degrees. This means that at the lunar poles, the Sun never rises more than a degree or two above the horizon. Crater rims and mountain peaks near the poles receive almost continuous sunlight. They are the so-called peaks of eternal light, elevated terrain that stays in sunlight for more than 90% of the lunar year, providing a potential source of near-continuous solar power for a lunar base. But the floors of craters near the poles, lying in the shadow of their own rims, never receive direct sunlight at all. These permanently shadowed regions, or PSRs, have temperatures that can fall below 130 Kelvin, colder than the surface of Pluto in some cases, and have remained in permanent darkness for billions of years. In those permanent shadows, water ice has accumulated. The ice comes from multiple sources: comets and water-bearing asteroids that have struck the Moon over billions of years, solar wind hydrogen reacting with oxygen and lunar minerals to form water molecules, and possibly volcanic outgassing from the lunar interior. The water molecules, created or deposited on the warmer sunlit regions of the Moon, migrate across the surface through ballistic hops, individual molecules traveling in short arcs through the lunar exosphere, until they reach the cold traps of the permanently shadowed craters, where temperatures are low enough that water ice is thermodynamically stable on timescales of billions of years. Once there, the ice stays. It accumulates, buried under a layer of dry regolith, mixed with the dust and soil of the crater floor. The first direct evidence for water ice at the lunar South Pole came from the Lacrosse mission in 2009, in which a spent Centaur rocket stage was deliberately crashed into the permanently shadowed Cabeus crater near the South Pole, creating an impact plume that was analyzed by the accompanying Lacrosse spacecraft and by the Lunar Reconnaissance Orbiter. The spectroscopic analysis of the plume confirmed the presence of water ice, along with a range of other volatiles including hydrogen sulfide, ammonia, carbon dioxide, carbon monoxide, methanol, and other compounds that were concentrated in the cold trap. Subsequent analysis of data from the Lunar Prospector Neutron Spectrometer, the Chandrayaan-1 Moon Mineralogy Mapper, and other instruments has built up a picture of water ice deposits at both poles, deposits that are patchy and inhomogeneous, mixed with regolith rather than forming pure ice sheets, but present in quantities that may total hundreds of millions of tons across both polar regions. The significance of water ice at the lunar South Pole for human exploration cannot be overstated. Water is heavy and expensive to launch from Earth. Every kilogram of water carried from Earth to the lunar surface costs tens of thousands of dollars in launch costs. On the Moon, water serves not only as a direct life support resource, drinking water, water for hygiene, water for growing food, but as a feedstock for propellant production. Water electrolysis, the splitting of water molecules into hydrogen and oxygen using electrical power, produces liquid hydrogen and liquid oxygen, which are the propellants used in the most efficient rocket engines, including the RS-25 engines of the SLS and the Merlin engines of SpaceX's Falcon rockets. A lunar base capable of extracting water ice from permanently shadowed craters, processing it into hydrogen and oxygen, and liquefying those gases for storage has, in principle, the ability to fuel spacecraft for missions to Mars and elsewhere without carrying that propellant from Earth. The Moon, in this vision, is not just a destination but a propellant depot, a refueling station at the edge of the Earth-Moon system that dramatically reduces the cost of deep space exploration. The specific crater that has emerged as the primary candidate for the Artemis landing site is Shackleton Crater in its associated region, a large impact crater approximately 21 kilometers in diameter at the lunar South Pole, whose rim is among the peaks of near-eternal light while its floor is permanently shadowed. The rim of Shackleton receives sunlight for more than 80% of the lunar year, providing a potential platform for solar power generation. The floor of the crater, in permanent shadow at temperatures below 200 Kelvin, contains some of the best characterized water ice deposits near the South Pole. The terrain between the rim and the floor, and the broader region around the crater, offers a range of scientific targets, ancient impact melt sheets, volcanic materials, highland terrain, that make it a geologically interesting region independent of its resource potential. The extraction of water ice from permanently shadowed craters presents engineering challenges that have no precedent in human spaceflight. Working in permanent darkness at temperatures below 200 Kelvin, in terrain of unknown regolith consistency, using equipment that must function without sunlight for power and without any ability to observe from above, is a fundamentally different operating environment than any previous lunar or planetary surface mission. The proposed approaches include heated excavation equipment that can penetrate the frozen regolith, volatile capture systems that heat the excavated material to release the water ice, and electrolysis systems that split the recovered water into hydrogen and oxygen for storage. All of these systems must function at extremely low temperatures, with no ability for rapid human repair if something goes wrong, in the most challenging terrain on the Moon. The engineering development required is substantial, and the robotic precursor missions, including NASA's Viper rover, which was designed to characterize the distribution and depth of water ice in the South Pole region, are aimed at reducing the uncertainty before humans arrive. The permanently shadowed craters of the lunar South Pole also contain something beyond water, a record of the early solar system that is preserved nowhere else in the inner solar system. The volatile compounds trapped in the cold traps, the ammonia, the carbon compounds, the sulfur species alongside the water, include material delivered by comets and asteroids from the earliest period of solar system formation, preserved in a deep freeze for billions of years. Analyzing the chemistry of these deposits in detail would provide a window into the composition of the impactors that shaped the early solar system, including the impactors that may have delivered the water and organic compounds to the early Earth that made life possible. The lunar cold traps are not just a resource to be mined. They are a scientific archive of the earliest history of our solar system, and the presence of astronauts with geological training and sophisticated analytical instruments at the South Pole represents a scientific opportunity that robotic missions alone cannot fully exploit. As the lunar night falls over the equatorial regions of the Moon, a night that lasts for 2 Earth weeks, during which temperatures drop to -170 degrees Celsius and any unheated hardware will freeze, the South Pole maintains its permanent character. The peaks of eternal light continue to gather sunlight. The shadowed crater floors continue their patient cold. The ice waits in the dark, as it has waited for billions of years, for the warmth and light that will finally arrive not from the sun but from a habitat and an excavator in the hands of the people who have come, at last, to use it. The engineering of in situ resource utilization, ISRU, the formal term for using local materials to sustain a space mission rather than depending entirely on supplies from Earth, is the central enabling technology for any permanent lunar presence. Water ISRU is the most immediate application, but the Moon's regolith offers other resources as well. The lunar soil contains significant concentrations of oxygen-bound and metal oxides, ilmenite, pyroxene, olivine, and other minerals that can be reduced by hydrogen or carbon at elevated temperatures to release oxygen. The FL oxygen, first lunar oxygen, extraction systems being developed by NASA and European partners aim to demonstrate the production of oxygen from lunar regolith at the scale of a few kilograms per day in early demonstration missions, scaling up to the production rates needed to support a crew and produce propellant in later phases. The oxygen serves dual purpose: breathable air for the habitat and oxidizer for rocket propellant. The regolith itself, the loose, fragmented rock material covering the lunar surface, is a resource whose properties are only beginning to be understood at the South Pole specifically. The Apollo samples come entirely from equatorial regions, and the chemistry, mineralogy, and physical properties of South Polar regolith may differ significantly from the Apollo sample suite due to differences in the source rocks, the impact history, the solar wind exposure history, and the presence of volatiles mixed into the soil. The Viper rover and the subsequent commercial lunar payload missions dispatched to the South Pole region under NASA's Commercial Lunar Payload Services program are gathering in situ data on South Polar regolith properties that will be essential for designing the excavation, processing, and construction systems that a permanent base will require. Building on the Moon requires understanding the material you are building with, and the South Pole, for all its scientific and resource significance, is a region whose material properties remain, in important details, unknown. Building a permanent outpost on the Moon is not, at its core, a transportation problem. The rockets to get there exist or are being built. The capsules to carry the crew exist. The challenge is what happens after landing, the long, unglamorous, complex engineering project of creating an environment in which human beings can live, work, eat, sleep, and remain healthy not for a few days of geological sampling but for weeks, months, and eventually years. The moon is not a friendly environment. It is, in almost every physical parameter, hostile to human life. Understanding that hostility, and the engineering responses to it, is the beginning of understanding what a permanent lunar outpost actually requires. The most immediate physical hazard on the lunar surface is radiation. Earth is protected from the full flux of solar and cosmic radiation by two overlapping shields: the atmosphere, which absorbs most of the high-energy particles and photons from above, and the magnetosphere, the magnetic field generated by Earth's liquid iron outer core, which deflects charged particles from the solar wind and from galactic cosmic rays before they reach the atmosphere. The moon has neither. It has no atmosphere and essentially no global magnetic field. The surface of the moon receives the full, unshielded flux of solar radiation, including the energetic protons and heavy ions of solar particle events, which can produce radiation doses of tens to hundreds of millisieverts an hour during major solar storms, and the continuous background of galactic cosmic rays, high-energy particles from outside the solar system that arrive uniformly from all directions. The radiation dose on the lunar surface is approximately 200 millisieverts per year under background conditions, roughly equivalent to receiving a full-body CT scan every 5 to 10 days, or about 200 times the average annual dose from natural background radiation at sea level on Earth. During a major solar particle event, a coronal mass ejection from the Sun that produces a burst of energetic protons, the dose rate can spike dramatically within minutes. The Carrington event of 1859, the largest recorded solar storm in historical times, would have produced a lethal radiation dose on the unshielded lunar surface within hours. Astronauts on the moon during such an event without adequate shielding would face a serious risk of acute radiation syndrome. The primary radiation mitigation strategy for a lunar outpost is mass shielding, placing enough material between the habitat and the space environment to absorb or scatter the incoming radiation. The most effective shielding material per unit mass for the specific radiation environment of the lunar surface is hydrogen-rich material, because hydrogen nuclei are very efficient at breaking up the high-energy particles and cosmic rays through a process called nuclear spallation. Water is an excellent radiation shield, dense, hydrogen-rich, and dual use as a life support consumable. A habitat wall lined with water tanks would provide significant radiation protection while also storing the crew's water supply. An alternative approach uses the moon's own regolith. Piling 2 to 3 meters of lunar soil over a habitat provides substantial shielding against solar particle events and reduces the galactic cosmic ray dose to levels more comparable to those experienced by frequent airline passengers on long polar routes. The regolith approach has the advantage of using a material that is already present in enormous quantities at the landing site, requiring no launch from Earth. The architecture of lunar habitats under active development reflects these radiation constraints. Inflatable habitat modules, like those being developed by Sierra Space under the LIFE program and by various NASA commercial partners, can be launched in a compact configuration and expanded to large volumes on the lunar surface, then covered with regolith by robotic bulldozers for radiation shielding. The Lunar Habitat Demonstration Unit tested by NASA at Johnson Space Center is a hardshell habitat roughly the size of a studio apartment, with a central node connecting sleeping quarters, a laboratory area, a hygiene facility, and a small galley, the minimum functional space for a crew of 2 to 4 for missions lasting weeks to months. The architectural challenge is providing enough private space, enough functional workspace, and enough psychological variety, different rooms for different activities, visual connection to the outside, some degree of personal territory, in a volume that must be small enough to be transported to the moon and robust enough to maintain a shirt-sleeve environment at all times. The lunar day-night cycle imposes a second set of engineering challenges. At most locations on the moon, the day lasts for approximately 2 Earth weeks, followed by 2 weeks of continuous night. During the lunar day, temperatures on the equatorial surface can reach 120 degrees Celsius, hot enough to boil water. During the lunar night, surface temperatures drop to -170 degrees Celsius. A habitat must manage these extreme temperature swings, maintaining a comfortable interior temperature regardless of the external thermal environment. This requires thermal control systems of considerable sophistication, radiators to reject excess heat during the day, heating systems to maintain temperature during the night. At the South Pole, this challenge is partially mitigated. The permanently illuminated peaks receive near-continuous sunlight at a low angle, maintaining relatively stable temperatures of around -50 degrees Celsius, far less extreme than the equatorial temperature swings. The regolith itself presents a hazard that the Apollo astronauts discovered and that remains one of the most difficult engineering problems for long-duration lunar habitation: lunar dust. The particles of lunar regolith are extraordinarily fine, much finer than terrestrial dust, and because there is no wind or water on the moon, they have never been smoothed or rounded by erosion. Under a microscope, lunar dust particles look like tiny shards of glass, angular, jagged, and electrostatically charged by the solar wind. The electrostatic charge causes the dust to cling aggressively to every surface it contacts: spacesuits, visors, solar panels, heat radiators, optical instruments, mechanical joints. The Apollo astronauts found that after a single EVA, their suits were coated in gray dust that was impossible to fully remove, that the dust abraded the suit material and clogged the joints, and that it had an acrid smell, possibly from reactive surface sites on the freshly exposed particle faces, when brought inside the habitat. For a short Apollo visit, the dust was a nuisance. For a months-long outpost, it is a potential system-threatening problem. A heat radiator coated in dust loses efficiency, a solar panel coated in dust loses power output, an EVA suit with dust-fouled joints becomes dangerous to use. Mitigation strategies for lunar dust include airlock designs that minimize the amount of dust brought into the habitat interior, electrostatic dust deflection systems that use electric fields to keep dust off critical surfaces, and suit designs that minimize the suit's ability to accumulate and retain dust. But none of these is a complete solution, and the long-term management of lunar dust exposure, both for hardware and for human health, since inhaled lunar dust particles are a potential respiratory hazard of unknown long-term severity, remains an active research and engineering challenge. The moon is generous with its resources and patient with its visitors, but it is not a welcoming environment. It will resist, in its specific ways, every attempt to make it habitable. Making it habitable anyway is the project. Beyond the physical challenges, the psychological dimension of long-duration lunar habitation has received increasing attention as the reality of extended stays approaches. The Apollo astronauts were on the lunar surface for at most 3 days, too brief for the psychological stresses of long-duration isolation to develop significantly. crews on the International Space Station have demonstrated, through decades of continuous occupation, the range of psychological challenges that emerge over months in an isolated, confined environment: interpersonal conflict between crew members, loss of motivation in the absence of varied stimulation, sleep disruption from the artificial light environment, the gradual accumulation of minor irritants into significant morale problems. On the Moon, those challenges will be present alongside the additional stress of operating in a genuinely dangerous environment where a suit malfunction or a habitat breach can kill you very quickly. The design of a psychologically sustainable lunar habitat is as much an architectural and social challenge as a technical one. Crew selection for psychological compatibility and resilience, mission structure that provides variety and a sense of progress and accomplishment, communication with Earth for human connection beyond the crew, recreation and personal space within the habitat. All of these are being studied in Antarctic winter-over stations, submarine crews, isolated research bases, and dedicated habitat simulation facilities. The humans going to the Moon will be engineers, scientists, and medical professionals, but they will also be people who need to sleep well and laugh occasionally and feel that their work matters. Designing for that is part of what building a permanent outpost means. The Concordia Research Station in Antarctica, operated jointly by the French and Italian Antarctic programs at an elevation of 3,200 meters on the Antarctic Plateau, 900 kilometers from the nearest other human station, is the closest analog on Earth to the psychological conditions of a lunar or Mars outpost. A winter-over crew of approximately 13 people spends 9 months completely isolated, with no possibility of evacuation except in the most extreme medical emergency, in an environment that is simultaneously physically challenging and profoundly monotonous. The European Space Agency has run an extensive program of psychological and physiological research at Concordia precisely because its isolation, team size, and environmental extremity approximate the conditions of a long-duration space mission. The data from Concordia, on sleep quality, cognitive performance, interpersonal dynamics, and the behavioral adaptations to long-term isolation, directly inform the crew support systems and mission architecture being developed for Artemis and Mars missions. The concept of crew autonomy, the gradual, structured transfer of decision-making authority from Earth-based mission controllers to the crew itself, is one of the most important operational innovations required for long-duration deep space missions. On the ISS, mission control is available for immediate consultation on any technical or medical issue, and the crew's operational decisions are closely supervised by a large ground support team. On the Moon, a communication delay of a few seconds allows near real-time consultation. On Mars, a communication delay of up to 22 minutes one-way makes real-time advice impossible, and the crew must be trained and equipped to make complex medical and engineering decisions autonomously. The shift in the crew-ground relationship from supervised execution to autonomous command represents not just a training challenge but a cultural shift within space agencies that have operated under close supervision for their entire history. Building the frameworks, tools, and crew training programs that enable genuine autonomy without losing the institutional knowledge and support of the Earth-based teams is one of the quieter but most consequential aspects of deep space mission preparation. Mars is not always the same distance from Earth. Both planets orbit the Sun, but Mars orbits further out and more slowly, and the geometry of their relative positions changes constantly. At opposition, When Earth and Mars are on the same side of the Sun, the distance between them can be as small as 54 million kilometers during a particularly close opposition, or as large as 101 million kilometers during a distant one. When they are on opposite sides of the Sun, the distance can exceed 400 million kilometers. The average distance between Earth and Mars, taken over time, is approximately 225 million kilometers. At the speed of light, a radio signal takes between 3 and 22 minutes to cross that distance, depending on orbital geometry. A spacecraft launched toward Mars on a standard home and transfer orbit, the fuel-efficient trajectory that uses an elliptical path connecting Earth's orbit to Mars's orbit, takes between 6 and 9 months to arrive. 6 to 9 months. For comparison, the longest single spaceflight by a human being was the 437-day mission of Valery Polyakov aboard the Russian Mir space station in 1994 and 1995, a mission conducted in low Earth orbit, protected by Earth's magnetic field, within communication range of Earth at all times, with supply ships arriving regularly. A Mars transit mission is categorically different. Once a spacecraft bound for Mars passes beyond the protection of Earth's magnetosphere, within the first day of travel, the crew is exposed to the full interplanetary radiation environment for the duration of the transit. There is no resupply. There is no rescue mission possible. At the midpoint of the transit, turning around and returning to Earth would take as long as continuing to Mars. Communication delays of up to 44 minutes round trip mean that real-time assistance from Earth is impossible for medical emergencies or critical equipment failures. The crew is, in a very real sense, on their own. The radiation environment of interplanetary space is more severe than the already challenging radiation environment of the lunar surface. In transit between planets, there is no planetary body to block radiation from half the sky. The crew is exposed to galactic cosmic rays and solar particle events from all directions simultaneously. The galactic cosmic ray dose during a 9-month Mars transit has been estimated at approximately 300 millisieverts, equivalent to about 1,500 chest X-rays, on top of whatever dose is received on the Martian surface and during the return transit. The total mission dose for a surface stay of approximately 500 days, a conjunction-class mission, which waits for the next favorable launch window before returning, has been estimated at between 500 and 900 millisieverts, depending on the solar cycle phase during which the mission takes place. Current NASA career radiation dose limits for astronauts are set at levels intended to limit the excess lifetime cancer risk to 3%, limits that a Mars mission would approach or exceed with current shielding technology. Several strategies are being developed to reduce the transit radiation dose. The most straightforward is mass shielding. The spacecraft habitation module can be designed with walls of water tanks and polyethylene, a hydrogen-rich plastic that is effective at absorbing cosmic rays, surrounding the crew quarters. A water wall of approximately 30 to 50 centimeters would reduce the galactic cosmic ray dose by a factor of 2 to 3. Dedicated storm shelters, smaller, more heavily shielded spaces within the spacecraft where the crew retreats during solar particle events, which can be predicted hours in advance by solar monitoring satellites, would protect against the acute radiation spikes that represent the most immediate health risk. Advanced propulsion systems that shorten the transit time also reduce the total radiation dose. A nuclear thermal propulsion system, which heats propellant by passing it through a nuclear reactor rather than combusting it chemically, could potentially cut the transit time from 9 months to 4 or 5, roughly halving the transit radiation dose. Nuclear thermal propulsion has been studied and partially developed since the 1960s, when the NERVA program, Nuclear Engine for Rocket Vehicle Application, demonstrated nuclear thermal rocket engines in ground tests that achieved the performance characteristics needed for Mars missions. The program was canceled in 1973 as part of the same budget cuts that ended Apollo. NASA's current NTP program, begun in earnest in the late 2010s, is developing a new generation of nuclear thermal engines aimed at demonstrating flight capability in the early 2030s. The engines burn liquid hydrogen as propellant, heated by a uranium reactor to temperatures far higher than any chemical combustion process can achieve, producing a specific impulse, the measure of propellant efficiency, roughly twice that of the best chemical engines. This means that for a given amount of propellant, a nuclear thermal rocket can achieve twice the velocity change of a chemical rocket, enabling faster trajectories and larger payloads. The microgravity environment of the transit presents a second major physiological challenge. In zero gravity, the human body undergoes a cascade of adaptations that are beneficial for weightlessness but damaging for the eventual return to gravity. Bone density in the load-bearing skeleton, the spine, the hip, the femur, decreases at rates of 1 to 2% per month in microgravity, driven by the absence of mechanical loading that normally stimulates bone formation and inhibits bone resorption. Muscle mass, particularly in the legs and lower back, decreases rapidly without the constant work of supporting body weight against gravity. The cardiovascular system adapts to a reduced blood pressure gradient between the head and feet. In weightlessness, blood distributes more uniformly throughout the body, and the heart adapts by pumping less forcefully, a change that, on return to gravity, produces orthostatic intolerance, the inability to maintain adequate blood pressure when standing. Mitigation of microgravity effects during transit has been studied for decades, and the principal countermeasure is exercise, vigorous, structured exercise, typically 2 to 3 hours per day, using resistance exercise equipment designed to simulate the loading of weight-bearing exercise in zero gravity. Current ISS crew members exercise extensively and still experience significant bone and muscle loss over 6-month missions, partially mitigated by the exercise regime. The exercise countermeasures reduce the rate of deterioration but do not eliminate it. The definitive solution to microgravity physiology on a Mars mission would be artificial gravity, produced by rotating the spacecraft to create a centrifugal acceleration felt by the crew as weight. The technical challenges of incorporating a rotating habitation module into a practical Mars transit spacecraft are significant. The module must be large enough that the rotation rate needed to produce one gravity is not so fast as to produce nausea from the Coriolis effect, but conceptually straightforward, and artificial gravity has been a standard element of serious Mars mission architecture studies for decades. The psychological dimension of a 9-month transit in a confined spacecraft with a crew of 4 to 6 is, if anything, even more challenging than the radiation and microgravity physiology. The crew will be confined to a volume comparable to a small apartment, with the same people, for 9 months, with no possibility of escape or significant change of environment. Communication with Earth will involve delays that make real-time conversation impossible, gradually transitioning the crew from the psychologically supported state of having mission control available for immediate consultation to a state of genuine autonomy in which they make their own medical, technical, and mission decisions. The social dynamics of the small isolated group, the formation of subgroups, the emergence of interpersonal conflicts, the management of authority and decision-making, will be one of the most consequential factors in the mission's success. The research program for addressing these challenges includes long-duration isolation simulation studies, like the Mars 500 experiment in Moscow, in which 6 volunteers spent 520 days in a simulated Mars mission habitat in 2010 and 2011, and the behavioral health monitoring programs of current ISS missions. The lessons from these studies are being incorporated into crew selection criteria, mission structure design, and the communication protocols that govern the evolving relationship between a Mars crew and Earth support teams as communication delays increase. The people who fly to Mars will need to be not just physically capable and technically expert but psychologically resilient, relationally skillful, and capable of genuine autonomous leadership under the most extreme circumstances any humans have ever faced. The selection, training, and support of those people is as critical as the engineering of the spacecraft that carries them. Autonomous medical care is one of the most demanding requirements of a Mars transit mission. The crew will need to be capable of diagnosing and treating any medical emergency that arises: appendicitis, dental emergency, bone fracture, cardiac event, psychiatric crisis, without any possibility of evacuation or specialist consultation in real time. At least one crew member will have advanced medical training, and the spacecraft medical kit will be the most comprehensive ever carried on a human spaceflight. But the range of conditions that can arise over a 9-month transit is broad enough that no individual crew member can be expert in all of them. AI-assisted medical diagnosis systems, software that can query the crew's symptoms, review vital signs and laboratory data, and suggest diagnoses and treatment protocols, are being developed as a form of autonomous medical support that extends the crew's effective medical capability. Ultrasound machines that a crew member with minimal training can use to image internal organs, guided by remote assistance from physicians on Earth where the communication delay allows, and by onboard AI where it does not, are already part of ISS medical capability and will be further developed for deep space. The food system for a Mars transit mission is another dimension of the engineering challenge that intersects with psychology as much as with nutrition. Current ISS food consists primarily of prepackaged, thermostabilized meals, food processed to last for years without refrigeration. The nutritional quality is adequate, but the variety and hedonic quality, how much the crew actually enjoys eating it, declines significantly over long missions, contributing to the gradual loss of food intake and body mass that has been documented in long-duration ISS crews. For a 9-month transit and a surface mission lasting more than a year, the food system must maintain crew nutrition and, equally important, crew morale. Fresh food, grown in the habitat, has been shown in ISS studies to have effects on crew well-being that go beyond its nutritional contribution. The smell of growing plants, the act of tending them, the sensory variety of a freshly grown salad leaf compared to a rehydrated meal pouch, these small pleasures are not trivial on a mission where every other sensory input is controlled and repetitive. After 6 to 9 months of transit through interplanetary space, months of radiation monitoring and exercise and carefully rationed resources, and the slow adjustment to being genuinely alone in the universe, the spacecraft approaches Mars. The planet grows from a small reddish dot to a disk, then to a world, its polar ice caps and ochre deserts and darker volcanic regions becoming visible as the distance closes. And then begins the most dangerous 7 minutes in human spaceflight, the entry, descent, and landing sequence, EDL, during which the spacecraft must slow from its interplanetary arrival velocity of roughly 20 to 25,000 kilometers per hour to a gentle touchdown on the Martian surface, using a combination of atmospheric drag, parachute deployment, and powered descent, in an atmosphere thin enough to be nearly useless and dense enough to be destructive. The Martian atmosphere is the central engineering challenge of Mars EDL. It has a surface pressure of approximately 6 to 10 millibars, less than 1% of Earth's sea level atmospheric pressure, which means it is far too thin for a parachute alone to slow a heavy spacecraft to landing speed. A parachute large enough to land even a modest Mars payload in the current Martian atmospheric density would need to be impractically enormous. But the atmosphere is also not a vacuum. It is thick enough to create severe aerodynamic heating during high-speed entry, reaching temperatures of hundreds of degrees Celsius on the spacecraft's heat shield as it decelerates through the upper atmosphere. The atmosphere is just barely useful enough for aerodynamic deceleration and just too thin for parachute-only landing, a designer's nightmare. Every Mars landing to date has solved this problem through a different combination of heat shield, parachute, and terminal deceleration system. The Viking landers of 1976 used large parachutes deployed after heat shield entry, followed by retrorocket firing for final touchdown. The Mars Pathfinder mission in 1997 and the subsequent Spirit and Opportunity rovers used airbags. The spacecraft was surrounded in a cocoon of inflated airbags that allowed it to bounce across the Martian surface for several hundred meters before coming to rest. The Curiosity rover, arriving in 2012 as the heaviest payload yet landed on Mars at nearly 1 metric ton, used a sophisticated system called the Sky Crane. After heat shield entry and parachute deployment, a retrorocket-powered descent stage lowered the rover on cables to the surface, then flew away to a safe crash landing at a distance. The Perseverance rover, identical in mass to Curiosity, used the same Sky Crane system in 2021. The Sky Crane is an extraordinary piece of engineering, a descent stage that maneuvers autonomously over the landing zone, avoiding hazards detected by its terrain relative navigation system, and threads the rover precisely onto the surface using cables, then cuts the cables and flies clear. But it cannot scale to human missions. A crewed Mars lander will weigh not 1 metric ton but 20 to 40 tons or more, the habitat module, the life support consumables, the ascent vehicle propellant, the surface mobility equipment, and the crew themselves represent a mass budget that dwarfs anything previously landed on Mars by an order of magnitude. Landing that mass on Mars requires a fundamentally different approach. The leading approach for human Mars EDL is a large aeroshell, a blunt-nosed, aerodynamically shaped heat shield covering that generates lift as well as drag during atmospheric entry, allowing the spacecraft to maneuver and target a specific landing zone, combined with a propulsive terminal descent phase using large rocket engines. SpaceX's Starship architecture proposes to use the Starship vehicle itself as the aeroshell, entering the Martian atmosphere belly first to maximize the aerodynamic cross-section and decelerate as much as possible using atmospheric drag, then pitching to a vertical orientation in the final seconds of descent for a propulsive landing on its Raptor engines. NASA's design reference mission for a crewed Mars landing has evolved through multiple versions, but all recent versions include a large aeroshell and a substantial propulsive descent system. The 7-minute communication delay between Earth and Mars, approximately 6 to 22 minutes one-way depending on orbital geometry, up to 44 minutes round-trip, means that the entire EDL sequence is autonomous. By the time Mission Control on Earth receives the signal that EDL has begun, the spacecraft will already have landed or crashed. Every decision in the EDL sequence must be made by the spacecraft's onboard computers based on pre-programmed algorithms and real-time sensor data, with no possibility of human intervention from Earth. This autonomy requirement has driven the development of increasingly sophisticated terrain-relative navigation systems, cameras and LiDAR sensors that compare the terrain below the descending spacecraft to a preloaded map and adjust the trajectory to avoid hazards and target the safest landing zone within the pre-selected site. For a crewed landing, the stakes of the 7-minute sequence are entirely different from a robotic mission. A crashed robotic lander is a scientific and financial loss. A crashed crewed lander is a human catastrophe. The reliability requirements for crewed EDL are correspondingly higher: multiple redundant systems, abort options at each phase of descent, crew capability to intervene in the final moments of descent if the autonomous system identifies a problem it cannot resolve. The design of a reliable, abort-capable crewed Mars EDL system is one of the hardest unsolved problems in Mars mission architecture, and its solution will require extensive testing, including multiple uncrewed landings of full-scale hardware at Mars before any crew attempts the sequence. Mars has its own meteorological hazard for landing: dust storms. The Martian surface is subject to local dust storms that develop into regional and sometimes planet-wide storms lasting weeks or months. During a global dust storm, the opacity of the atmosphere increases dramatically, reducing solar power availability, cutting visibility to near zero, and altering the density profile of the atmosphere in ways that affect EDL ballistics. The global dust storm of 2018, which ended the Opportunity rover mission by blocking enough sunlight to deplete its solar panels, lasted approximately 3 months and reduced insolation, the solar energy reaching the surface, by more than 90% in some areas. A crewed landing attempted during a regional dust storm could face altered atmospheric density that affects the parachute deployment altitude and the propulsive descent fuel budget, and could arrive at a landing site with near-zero visibility. Mission planning for crewed Mars landings must account for dust storm season, and the habitat and base design must be capable of surviving extended periods with minimal solar power. But the landing, once achieved, is an extraordinary moment. The dust from the retrorocket engines settling. The engines falling silent. The first pressure readings from the onboard sensors confirming that the spacecraft is intact, the habitat is sealed, the life support is functioning. The first view from the cameras, the rust-red surface of Mars, the salmon-colored sky at local time of day, perhaps a few rocks visible through the dust haze, the horizon further and lower than on Earth because Mars is a smaller world. After 6 months in the dark of space, after the 7 minutes of terror, after all the years of training and preparation and waiting, there it is. Another world. The surface of Mars. The crew has arrived, and the next chapter of the human story begins. The first hours after landing are the most critical of the surface mission. Before anyone opens a hatch or considers stepping outside, the crew must conduct a detailed systems check, verifying the integrity of every habitat structure, every life support component, every power system, every communication link. The landing itself, however precisely executed, subjects the spacecraft to mechanical stresses that can shift hardware, crack seals, and disturb pre-positioned equipment. The checklist for post-landing systems verification for a Mars mission is estimated to require approximately 48 hours to complete, 2 Martian days, called sols, before the crew can be confident that the habitat is safe for extended occupation. Those first 2 sols, in a habitat that has just survived entry, descent, and landing on Mars, are not a time for celebration. They are a time for methodical, patient verification of every system that will keep the crew alive for the next year and a half. The Martian day, the sol, is 24 hours and 37 minutes long, close enough to the Earth day that human circadian rhythms adapt relatively easily. This is a significant advantage over the Moon, where the 2-week day-night cycle has no analog in human biological experience. Crews on Mars can maintain a near-normal daily schedule, with morning and evening and night, with the regular rhythm of waking and sleeping that anchors human psychology. The Martian year, however, is approximately 687 Earth days, nearly twice as long as an Earth year. A crew waiting for the next favorable launch window to return to Earth will experience an entire Martian year on the surface, watching the seasons change, because Mars, like Earth, has an axial tilt, and has spring and summer and autumn and winter, though driven by a more eccentric orbit that makes the southern summer shorter and warmer and the northern summer longer and cooler than their Earth counterparts. The crew will be there long enough to observe those seasons change. Long enough to feel what it means to live on another world, not just visit it. Mars is, in many ways, a familiar world. It has mountains and valleys and plains and polar ice caps. It has seasons and weather and a daily cycle of light and dark. Its day is almost exactly as long as Earth's. Its axial tilt is similar to Earth's, producing analogous seasonal variations in sunlight across its hemispheres. It has clouds, thin, wispy water ice clouds that form at altitude in the Martian morning and burn off as the day warms. It has weather systems, not the complex, moist convective weather of Earth, but dust devils and cyclonic storms and diurnal wind patterns driven by the heating and cooling of the surface. In these respects, Mars is more Earth-like than any other body in the solar system. And yet the specifics of the Martian surface, its chemistry, its geology, its weather extremes, its deep and ancient history, constitute a world of extraordinary strangeness, a planet that followed a different evolutionary path from Earth with consequences that are written in every rock and dune and canyon. The surface of Mars is dominated by iron oxide, rust, which gives the planet its characteristic red color. The Martian regolith is a mixture of basaltic rock fragments, iron oxide minerals, and fine dust particles that coat every surface and are responsible for the reddish tint of the sky as well as the ground. The iron was oxidized not by biological oxygen, as iron rusts on Earth, but by chemical reactions between iron-bearing minerals and water or atmospheric oxidants early in Mars's history. The rust is, in a sense, a geological record of a wetter, chemically more active past, the signature of a planet that once had liquid water in abundance and the chemistry that goes with it. The geology of Mars is divided into three broad periods. The Noachian period, spanning from Mars's formation approximately 4.5 billion years ago to roughly 3.7 billion years ago, was the era of heavy bombardment and, critically, liquid water. The ancient highlands of the southern hemisphere, heavily cratered and ancient, preserve the record of this period. River valleys, lake beds, and deltaic deposits visible from orbit in the Noachian terrain show unambiguously that liquid water flowed on the Martian surface for hundreds of millions of years. The Hesperian period, from about 3.7 to 3 billion years ago, was a transitional era during which Mars was losing its atmosphere and surface water was becoming episodic rather than continuous, the era of catastrophic floods, where enormous quantities of water released suddenly from subsurface ice or permafrost carved the vast outflow channels of the northern lowlands. The Amazonian period, from 3 billion years ago to the present, is the cold, dry, and geologically quiet era in which Mars has remained ever since, the era of the Mars we see today. The most dramatic geological feature on Mars, and in the solar system, is Olympus Mons, a shield volcano approximately 22 kilometers high and 600 kilometers wide. It is the tallest mountain in the solar system by most measures, standing nearly 3 times the height of Mount Everest above the surrounding terrain. Its summit caldera, the collapsed magma chamber at its top, is 80 kilometers across and 3 kilometers deep. Olympus Mons formed over billions of years as the Martian tectonic plate, unlike Earth's moving plates, remains stationary over a volcanic hotspot in the mantle, allowing lava to pile up continuously without being carried away. Earth's largest shield volcanoes, Mauna Loa in Hawaii, the Canary Islands, the Galapagos, are relatively small because Earth's tectonic plates move, carrying the volcano away from its hotspot within millions of years. Mars has no plate tectonics. Its hot spots built their mountains for billions of years without interruption. The result is Olympus Mons, a mountain so large that its base is over the horizon from its summit, and a crew standing on the summit would not realize they were on a mountain at all. The slope is so shallow, approximately 3 degrees, that the curvature of Mars hides the base below the horizon. Adjacent to Olympus Mons is the Tharsis Bulge, a vast elevated plateau roughly the size of North America, raised 4 kilometers above the mean Martian surface elevation by the accumulated volcanism of the Tharsis Volcanic Province. The weight of the Tharsis Bulge on the Martian lithosphere has deformed the crust around it, producing a radial pattern of fractures and canyons extending thousands of kilometers in all directions. The most spectacular of these is Valles Marineris, a canyon system that stretches approximately 4,000 kilometers along the Martian equator, reaches depths of up to 7 kilometers, and in places is 600 kilometers wide. To compare, the Grand Canyon is 446 kilometers long, 1.8 kilometers deep, and at most 29 kilometers wide. Valles Marineris is not merely a large canyon. It is a gash in the planetary surface that would stretch from the east coast to the west coast of the United States and would swallow the Grand Canyon as a minor tributary. It formed primarily by tectonic stretching and rifting of the crust in response to the Tharsis Bulge, rather than by river erosion, though liquid water flowed along parts of it in the Noachian period. The weather on Mars is driven by a thin atmosphere of primarily carbon dioxide, 95% of the Martian atmosphere, at a surface pressure of roughly 6 to 10 millibars. The thinness of the atmosphere means that wind, even at high velocities, carries very little energy compared to Earth wind. A 100 km/h Martian wind would be felt as a gentle breeze on Earth, because the air density is so low. But the Martian wind is effective at moving fine dust particles, and over billions of years the wind has shaped the Martian surface extensively. Vast fields of dark basaltic sand dunes cover the floors of craters and the lowland plains. Bright streaks of dust deposited by wind extend downwind of crater rims and mountains across enormous distances. The same wind that deposits dust also scours it, producing yardongs, wind-eroded ridges of soft rock aligned in the direction of the prevailing wind, that can be seen in the ancient sedimentary terrains near the poles. The dust storm season on Mars peaks during southern hemisphere summer, when Mars is near perihelion, its closest approach to the Sun, and the increased solar heating drives stronger convective and advective winds. Regional dust storms develop when surface heating lifts dust into the atmosphere, which absorbs solar radiation and heats further, driving stronger winds that lift more dust in a self-amplifying cycle. Occasionally, regional storms merge and expand to cover the entire planet in a global dust storm that persists for weeks or months, reducing surface insulation dramatically and cooling the surface while warming the middle atmosphere. The 2018 global dust storm, which ended the Opportunity rover mission, lasted approximately 3 months and at its peak reduced visible sunlight at the surface to a level comparable to a heavily overcast day on Earth. For a Mars surface base that depends on solar power, a global dust storm is an existential threat that demands either nuclear power, very large battery storage capacity, or a combination of both. The subsurface of Mars is increasingly understood to be geologically complex and potentially still active. Ground-penetrating radar data from the Marses and Shurud instruments on Mars orbiters have revealed subsurface layered deposits, buried impact craters, and, controversially, what may be subsurface liquid water at the base of the South Polar ice cap, where the pressure and the presence of dissolved salts could keep water liquid despite the extreme cold. The Mars seismometer CEIS aboard the InSight lander, operating from 2018 to 2022, detected hundreds of Mars quakes, seismic events ranging from small microseismic tremors to larger events equivalent to approximately a magnitude 5 earthquake, confirming that Mars is seismically active, though far less so than Earth. The distribution of Mars quake sources suggests that the Cerberus Fossae region, a series of young tectonic fractures east of the Tharsis Bulge, is a zone of active tectonism and possibly recent volcanism. Mars may not be geologically dead. It may simply be quiet, on geological timescales, between episodes of activity. For the first humans on the Martian surface, the landscape will be simultaneously recognizable and alien. The horizon, closer than Earth's due to Mars's smaller radius, will give the landscape a different geometry. The sky will be a pale salmon pink during the day, the color of the dust-suspended atmosphere scattering reddish sunlight, and shift toward blue around the setting sun, the inverse of Earth's sky colors because the scattering dynamics of Martian dust work opposite to those of Earth's oxygen-nitrogen atmosphere. The silence will be profound, not the total silence of the moon, but a quiet so deep that the wind, even when it blows at tens of kilometers per hour, will be barely audible through a spacesuit. The light will be dimmer than Earth's, about 40% of Earth's surface illumination, but sufficient to read by, sufficient to work in. On a clear day, the crew might see Phobos, the larger of Mars's two small moons, an irregular captured asteroid, moving quickly across the sky from west to east, completing an orbit in less than 8 hours, rising in the west and setting in the east contrary to the moon's behavior from Earth. The other moon, Deimos, small and distant, will be barely distinguishable from a bright star. It will be a new sky, above a new world, experienced by human eyes for the first time. The ancient ocean hypothesis, the idea that the northern lowlands of Mars were once covered by a large body of liquid water, has been debated for decades and remains scientifically unresolved. The northern lowlands sit approximately 5 kilometers lower in elevation than the southern highlands, and their smoother, less cratered surface suggests they were resurfaced by some process, possibly by sediment deposition in a shallow sea, in the Noachian or early Hesperian period. The proposed shorelines, terrace-like features visible in orbital imagery at roughly consistent elevations around the boundary of the lowlands, are geomorphologically plausible but not definitively established. If the Northern Ocean existed, it would have covered approximately a third of the Martian surface, comparable in area to the Arctic Ocean. The water that filled it has been lost to space through atmospheric escape of water vapor driven by solar ultraviolet radiation, and to the subsurface, frozen as permafrost and possibly as liquid water deep in the crust. The rocks of the ancient shorelines, if they exist, are the geological witnesses to a Mars that was, for a brief period in its early history, genuinely ocean-covered and potentially habitable. The Jezero crater landing site of the Perseverance rover was selected precisely because it preserves, in extraordinary detail, the geological record of a time when liquid water was present. Jezero is a 35-kilometer diameter impact crater in the western edge of Isidis Planitia that, approximately 3.5 billion years ago, contained a lake fed by 2 river systems entering from the west and northwest. The delta fan deposited by the western river is clearly visible from orbit, a classic fan-shaped sedimentary deposit spread across the crater floor where the river met standing water and its current slowed and dropped its sediment load. The Perseverance rover has been exploring this delta in detail since its landing in February 2021, drilling core samples from the ancient lake sediments and caching them for eventual return to Earth. The delta sediments are among the best possible samples for the search for ancient microbial life on Mars, fine-grained, water-deposited sediment with high concentrations of organic carbon, if any was present, and the kinds of mineral matrices that preserve biosignatures over geological time. The samples Perseverance is caching in the Jezero Delta may, when returned to Earth laboratories in the early 2030s, contain the answer to one of the oldest questions in planetary science. The first Mars base will arrive, in the most literal sense, before the first crew. The architecture of responsible Mars mission planning calls for pre-deploying habitats, power systems, and resource production equipment, landed robotically, activated and tested remotely from Earth, before any human being boards a Mars-bound spacecraft. The lessons of Antarctic exploration are instructive. No serious polar expedition arrives at an empty continent without prepositioned supplies and shelter. The distances and communication delays of Mars make the pre-deployment principle even more critical. If a habitat component fails after landing in before the crew arrives, there is time, months or years, to diagnose the problem, send a replacement, and verify the fix before anyone's life depends on it. If the same failure occurs after the crew has landed, there may be no good options. The first habitat modules will almost certainly be prefabricated structures launched from Earth and landed intact on the Martian surface. Inflatable habitat modules, rigid-walled tunnels and nodes supplemented by inflatable sections that expand to large volumes after landing, offer the best combination of launch compactness and surface volume. The TransHab concept, developed by NASA in the 1990s, later evolved into the Beam module on the International Space Station and Sierra Space's Life Habitat, is the intellectual ancestor of the Mars inflatable habitat systems now under development. A Mars habitat module in the current design reference architecture is a cylinder approximately 8 meters in diameter and 10 meters long in its deployed configuration, providing approximately 500 cubic meters of pressurized volume, enough for a crew of 4 to 6 to live and work for years without feeling critically cramped, though with none of the space luxury that surface life on Earth provides. The power system for a Mars base is a foundational constraint that shapes every other element of the architecture. Solar power at Mars receives about 40% of the sunlight available on Earth, and during dust storm season that fraction can drop to 10% or less. A Mars base that depends entirely on solar power must either carry enormous battery storage for dust storm survival, weeks or months of stored energy, or accept that it will be severely power limited and potentially life-threateningly cold during extended dust events. The alternative, which has been in the Mars mission architecture discussion since the 1980s and has moved increasingly to the center of the planning in recent years, is nuclear fission power. The Kilo Power Project, now formalized as the Fission Surface Power Project, is developing a compact nuclear fission reactor approximately 1.5 meters tall and 600 kilograms in mass that can produce 10 kilowatts of electrical power continuously, independent of sunlight and weather, for at least 10 years. 4 to 6 such units would provide the base power load for a small crewed Mars base. Unlike solar panels, a fission reactor buried under regolith for radiation shielding provides constant, reliable power regardless of dust storms, night, or surface degradation. In-situ resource utilization on Mars, ISRU, is not a luxury feature of the mission architecture. It is a survival requirement. The most critical ISRU product on Mars is oxygen, needed both for breathing and as the oxidizer component of the rocket propellant required to launch the crew off the surface and into Mars orbit for the return journey. Carrying the oxygen for the ascent vehicle from Earth would require launching an enormous additional mass. The oxygen for a Mars ascent vehicle represents hundreds of kilograms. Producing it locally from the Martian atmosphere is the alternative. The Martian atmosphere is 95% carbon dioxide. The Mars Oxygen In-Situ Resource Utilization Experiment, MOXIE, a small gold-plated box aboard the Perseverance rover, demonstrated for the first time in 2021 that oxygen can be produced from Martian carbon dioxide by a process called solid oxide electrolysis, passing the carbon dioxide over a heated ceramic electrode that strips away the oxygen atoms, combining them into molecular oxygen. MOXIE produced approximately 10 grams of oxygen per hour in its initial tests, a tiny quantity, barely enough to sustain a small dog, but a proof of concept that the fundamental chemistry works in the actual Martian environment. Scaling MOXIE technology to the quantities needed for a crewed mission, hundreds to thousands of kilograms of oxygen, requires a system hundreds of times larger, operating continuously for months before the crew arrives. The engineering scaling from a shoebox-sized demonstration to a refrigerator-sized operational system is substantial, but the physics and chemistry are established. A full-scale Mars ISRU oxygen production plant, running on nuclear fission power throughout the Martian winter and dust storm seasons without interruption, could produce enough oxygen for a crew of 6 and enough oxidizer for an ascent vehicle within approximately 14 months, the time between an early pre-deployment cargo landing and a subsequent crewed mission launch window. Water is the second critical ISRU resource on Mars. The Martian surface contains water ice in the polar regions and is permafrost mixed into the regolith at higher latitudes, and there may be near-surface ice at the planned landing site latitudes as well. Near the equatorial regions, which are more accessible for landing trajectory geometry, water is less abundant in the near surface but may be present in the subsurface. The Curiosity rover found hydrated minerals in the sedimentary rocks of Gale Crater, and neutron spectrometer data from Mars orbiters shows elevated hydrogen, indicative of water or hydrated minerals, at many locations across the surface. A Mars base will need to find and extract water from its local environment to supplement any water brought from Earth, both for life support and for the production of hydrogen fuel. Excavating frozen regolith and heating it to release the water, or drilling into the permafrost layer below the active regolith, are the approaches most likely to be pursued depending on the characteristics of the specific landing site. Three-dimensional printing with local materials, in situ construction, is one of the most actively developed technologies for Mars base expansion beyond the initial pre-deployed modules. The regolith of Mars, reduced to a fine powder and mixed with a binding agent, possibly sulfur, which is present in Martian soil and can be melted to form sulfur concrete when cooled, can be extruded by robotic printers to form structural building elements. Tests of sulfur concrete with simulated Martian regolith simulant have shown that it achieves compressive strengths comparable to standard Portland cement concrete, strong enough for structural applications, and is self-sealing, reforming its surface when damaged by heating. A robotic construction system that can excavate regolith, process it into sulfur concrete feedstock, and extrude habitats, walls, and berm structures autonomously would allow a Mars base to expand its pressurized volume and its radiation shielding without requiring material launched from Earth. The architecture of a mature Mars base, 10 to 20 years after the first human landing, in the planning documents of NASA and its partner agencies looks something like this: a central pressurized hub connected by tunnels to a series of specialized modules, a laboratory for scientific work, a medical bay, a greenhouse for food production, crew quarters, a workshop for equipment maintenance and fabrication. Around the hub, surface infrastructure, solar panels and nuclear reactors for power, ISRU plants for oxygen and water and propellant production, equipment storage and vehicle garages, landing pads for arriving and departing spacecraft. Covering the habitat modules, a layer of regolith berm constructed by robotic bulldozers for radiation shielding. Surrounding the entire complex, a perimeter of monitoring sensors and environmental instruments. And beyond the perimeter, in every direction, the Martian surface, ancient, enormous, and full of scientific questions that only the humans inside the habitat can answer. Rest with that image for a moment. A base on Mars. Not a temporary camp but a permanent installation, with power and water and food and science, built from the resources of the planet it sits on, connected to Earth by radio waves that take minutes to cross the distance, inhabited by people who have committed to being somewhere that no human has ever been before. It exists in the planning documents, in the engineering simulations, in the hardware already being built and tested. It does not yet exist on Mars. But the gap between those two states, the paper and the ground, is narrower than it has ever been. The human body was not designed for space. It was designed by 4 billion years of evolution for the specific conditions of Earth's surface, a gravitational field of 1 g pulling continuously downward, an atmosphere of 78% nitrogen and 21% oxygen at 1 bar of pressure, a moderate temperature range, and a radiation environment heavily filtered by the atmosphere and magnetosphere above. Every organ system in the human body reflects these conditions. The skeleton exists to resist gravity. The cardiovascular system pumps blood against gravity to maintain adequate pressure in the brain. The vestibular system uses gravity as its reference for orientation. The circadian rhythm is entrained to Earth's 24-hour day. Remove any of these conditions, reduce gravity, remove atmospheric pressure, change the radiation environment, alter the light-dark cycle, and the body begins to adapt, sometimes helpfully, sometimes with consequences that accumulate into medical problems of serious concern. The most extensively studied consequence of long-duration spaceflight is bone loss. In microgravity, the mechanical loading that normally stimulates bone formation is absent. Bones no longer need to support body weight, and the biological signals that maintain bone density in response to loading disappear. The result is osteoclastic resorption. The cells that break down bone tissue, osteoclasts, continue their work, while the cells that build bone, osteoblasts, reduce their activity. The net effect is a loss of bone mineral density in the load-bearing skeleton, the spine, the hip, the femur, of approximately 1 to 2% per month in microgravity. Over a 6-month ISS mission, an astronaut who exercises rigorously may lose 8 to 12% of hip bone density. Over an 18-month Mars mission, including the 6 to 9-month transits in microgravity and the approximately year-and-a-half surface stay in Martian gravity, which is 38% of Earth's, the cumulative bone loss could approach levels associated with severe osteoporosis in older adults, with substantially elevated fracture risk on return to Earth's gravity. The countermeasures currently employed on the ISS, primarily resistive exercise using the Advanced Resistive Exercise Device, or ARD, a sophisticated exercise machine that uses vacuum cylinders to simulate free weights in microgravity, reduce the rate of bone loss significantly compared to early space flights, when exercise countermeasures were less rigorous. Combined with pharmacological interventions, bisphosphonates, drugs that inhibit osteoclast activity, have been tested in spaceflight and show promise for reducing bone resorption without requiring hours of exercise. The current countermeasure suite can limit bone loss to a few percent per 6-month mission in well-compliant crew members. But scaling these approaches to an 18-month Mars mission, and ensuring compliance and effectiveness in an environment where the exercise equipment itself must function perfectly for the entire duration without Earth-based servicing, remains a significant challenge. Muscle atrophy in microgravity follows a similar pattern. The postural muscles, those used in daily life to maintain upright posture against gravity, lose mass rapidly in weightlessness because they are no longer required to do their primary job. The leg muscles, back muscles, and core musculature that supports standing and walking shrink dramatically without the continuous low-level exercise of just moving through a gravity field. Vigorous resistive exercise mitigates this atrophy, but not completely, and the functional consequences, weakness, fatigue, reduced endurance, accumulate over long missions. On arrival at Mars, after 6 to 9 months of transit in microgravity, the crew must transition immediately to operating in Martian gravity, 38% of Earth's, in a spacesuit on an EVA schedule, before their muscles have had time to recover. The physiological demands of the landing phase operations, when the base is being set up and the crew is most active but also most physically compromised, represent one of the most challenging periods of the entire mission from a human factors perspective. A less well-known but increasingly concerning consequence of long-duration spaceflight is spaceflight-associated neuroocular syndrome, SANS. Approximately 40 to 60% of astronauts on long-duration ISS missions show evidence of structural changes in the eye and brain after their missions: flattening of the back of the eyeball, swelling of the optic disc, changes in the optic nerve sheath, and in some cases small lesions in the white matter of the brain visible on MRI. Many of these astronauts also experience vision changes, a shift toward farsightedness that in some cases persists years after the mission. The cause of SANS is believed to be the cephalad fluid shift that occurs in microgravity. Fluid that normally pools in the legs under Earth's gravity redistributes throughout the body and accumulates slightly in the head, increasing intracranial pressure chronically. This chronic elevated pressure is transmitted through the optic nerve sheath to the eye, gradually deforming the ocular structures. SANS has been identified as one of the most significant human health risks for long-duration spaceflight, particularly for Mars missions where the cumulative exposure is far greater than any ISS mission. Countermeasures being studied for SANS include lower body negative pressure devices, essentially a vacuum suit worn over the legs that draws fluid downward from the head, simulating the effect of gravity on fluid distribution, and pharmacological approaches to reduce intracranial pressure. Neither approach is yet sufficiently validated for deployment on a Mars mission, and the search for effective SANS mitigation is one of the most active areas of space medicine research. Artificial gravity during the transit phase would likely mitigate SANS, since the fluid shift is driven by the absence of gravity, a hypothesis that cannot yet be tested on humans due to the absence of a rotating spacecraft capable of carrying a crew. The immune system is also affected by long-duration spaceflight in ways that are not fully understood. Multiple studies of ISS crew members have found evidence of immune dysregulation, changes in the distribution and function of immune cell populations, reactivation of latent herpes viruses that are normally kept dormant by immune surveillance, and altered inflammatory responses. The causes are multifactorial: the radiation environment, the microgravity-induced changes in fluid dynamics and cell mechanics, the psychological stress of isolation, the disruption of normal sleep and circadian rhythms, and the confined habitat environment all contribute. The net effect is a crew that is, in various measurable ways, immunologically compromised relative to their pre-flight baseline. On a Mars mission, with no possibility of evacuation and limited pharmaceutical resupply, managing the immune consequences of long-duration spaceflight is a medical priority with life-or-death implications. Sleep disruption is one of the most consistently documented effects of long-duration spaceflight, and one of the most consequential for mission performance. ISS crew members chronically undersleep. Average sleep duration on orbit is approximately 6 hours per night compared to the recommended 7 to 9, due to a combination of noise from the station's environmental control systems, the difficulty of maintaining a stable circadian rhythm in an environment where the sun rises and sets every 90 minutes as the station orbits Earth, the schedule pressure of packed activity plans, and the psychological difficulty of relaxing completely in an environment where any system's failure requires immediate response. Chronic sleep deprivation degrades cognitive performance, emotional regulation, immune function, and physical recovery from exercise. On a Mars mission, the consequences of impaired judgment from sleep deprivation, in a crew making autonomous medical and engineering decisions in a life-critical environment, are far more severe than on the ISS, where mission control can catch errors that a tired crew member misses. What the accumulated data from decades of human spaceflight tells us is that the human body is not a passive payload to be carried to Mars and back. It is a dynamic biological system that responds to every aspect of the space environment: gravity, radiation, pressure, light, temperature, social context, sleep schedule, and requires active, continuous management to remain functional over a mission duration of 18 months or more. The medicine of long-duration spaceflight is not a problem to be solved once and then ignored. It is an ongoing practice of monitoring, intervention, and adaptation, conducted by a crew that is simultaneously the patient and the physician, in an environment that tests every dimension of human physiology simultaneously. Understanding that practice, building the protocols, the tools, the training, and the pharmacopoeia that make it possible, is one of the most important and most underappreciated aspects of the road to Mars. The twin studies conducted by NASA using astronaut Scott Kelly and his identical twin brother Mark, Scott flying a year-long ISS mission from 2015 to 2016 while Mark remained on Earth, provided the most comprehensive comparison of the biological effects of long-duration spaceflight ever undertaken. The analysis of the twins' genomes, epigenomes, microbiomes, cognitive performance, and physiological measurements showed that while Scott's core genome was essentially unchanged, his gene expression, which genes were active and at what levels, shifted measurably during spaceflight and had not entirely returned to pre-flight baseline even 2 years after landing. His telomeres, the protective caps on chromosome ends, often used as a marker of cellular aging, actually lengthened during spaceflight, opposite to the expected direction, then shortened rapidly on return to Earth. His cognitive performance showed modest decline on several measures during the mission and partial recovery afterward. His gut microbiome changed substantially during flight. The study, published in its full synthesis in Science in 2019, underscored that spaceflight affects human biology at every level simultaneously, from the molecular to the cognitive, and that the full extent of those effects and their long-term consequences are still being characterized. The body of knowledge being built from ISS research, twin studies, bed rest analogs, and centrifuge experiments is the scientific foundation on which Mars mission medicine will stand. It is incomplete. The definitive answers about SAN's progression over 18 months, about bone loss mitigation at Martian gravity, about immune function over a full mission, will not be available until the mission itself is flown. There is an irreducible component of risk in going to Mars that cannot be trained away or engineered away. The first Mars crew will carry that risk with full awareness. That awareness, and the willingness to proceed despite it, is part of what makes the project genuinely courageous rather than merely technically ambitious. A Mars crew of 6 people requires approximately 600 kilograms of food per person per year, roughly 3,600 kilograms of food for the entire crew for a single year of surface operations. Adding the food needed for the 9-month transit to Mars and the 9-month return, a complete Mars mission with a surface stay of approximately 500 days requires something in the neighborhood of 9,000 kilograms of food, plus packaging and water for rehydration of dried items. At current launch costs, even with the dramatic reductions that SpaceX Starship aims to achieve, that represents an enormous financial burden and a critical single point of failure. If the food supply is compromised, by contamination, by packaging failure, by a supply mission that doesn't arrive, the crew faces starvation. The solution that space system designers have been working toward for decades, and that is now moving from concept to demonstration, is growing food in space rather than carrying it. The concept of a bioregenerative life support system, a closed-loop ecology in which plants and microorganisms and human metabolism are integrated into a system that recycles air, water, and nutrients with minimal input from outside, has been the philosophical ideal of space life support since the earliest days of human spaceflight. The basic principle is elegant. Plants use carbon dioxide and water to produce oxygen and organic matter through photosynthesis. Humans consume oxygen and organic matter and produce carbon dioxide and water and organic waste. The organic waste is broken down by microorganisms and returned to the plant growth medium as nutrients. In a perfectly closed system, the only inputs required are light, energy, and trace minerals, and the only outputs are heat. In practice, real bioregenerative systems are never perfectly closed, but they can achieve high degrees of closure that dramatically reduce the resupply burden. The advanced plant habitat aboard the International Space Station, a sealed growth chamber the size of a large microwave oven, equipped with LED lighting in multiple wavelengths, automated watering, atmospheric control, and real-time monitoring, has been used to grow dwarf wheat, radishes, peppers, leafy greens, and other crops in microgravity since its installation in 2018. The VEG-04 and VEG-05 experiments with red romaine lettuce demonstrated that microgravity-grown lettuce is nutritionally equivalent to Earth-grown lettuce and, critically, that crew members who consumed their own grown lettuce reported measurable improvements in mood and well-being compared to periods when they were eating only pre-packaged food. The psychological benefit of growing and harvesting fresh food in space is disproportionate to its caloric contribution. The act of tending plants, the smell of living vegetation, the texture and flavor of a fresh leaf in an environment where every other sensory experience is controlled and artificial, provides a form of psychological nourishment that packaged food cannot replicate. The plant species most suitable for space agriculture share several characteristics: high caloric or nutritional density per unit of growing area, short growth cycle to minimize time between planting and harvest, tolerance for the reduced light levels and unusual atmospheric compositions of a spacecraft or habitat, and edibility of most of the plant mass. Crops where the majority of the plant biomass is food rather than an edible stalk or root. The current leading candidates for a Mars food production system include wheat, for its caloric density and adaptability, soybeans, for protein and fat content, sweet potatoes, for their extraordinary caloric yield per unit area and nutritional completeness, leafy greens, for micronutrients and psychological variety, and dwarf legumes such as cowpeas and bush beans. No single crop provides complete nutrition, but a carefully designed polyculture of 5 to 8 species can provide a nutritionally adequate diet for a small crew. Lighting is the primary energy cost of space agriculture. Plants require photosynthetically active radiation, light in the wavelengths that chlorophyll absorbs, at sufficient intensity and duration to drive photosynthesis at productive rates. LED lighting systems designed for space agriculture have been optimized to emit primarily the red and blue wavelengths that are most efficiently used by chlorophyll, minimizing wasted energy in wavelengths that plants do not use. Even so, the energy budget for growing enough food to significantly supplement a Mars crew's diet is substantial. Estimates suggest that providing 50% of a crew's caloric intake from in-situ agriculture would require several hundred kilowatts of electrical power dedicated to lighting, on top of the power requirements for habitat climate control, life support, ISRU operations, and scientific equipment. This reinforces the importance of nuclear fission power for a Mars base. Solar panels alone, degraded by dust and limited by the 40% of Earth's insolation available at Mars, would struggle to provide the power budget that a fully functional, food-producing base requires. The growth medium for space agriculture has received sustained research attention. Hydroponic systems, growing plants in nutrient-enriched water without soil, offer precise control of nutrient delivery, high water use efficiency, and compatibility with the closed-loop water recycling systems of a spacecraft life support system. Aeroponic systems, which deliver nutrient solution as a fine mist to bare roots hanging in air, are even more water efficient than hydroponics and have been tested on the ISS with promising results. The alternative, growing plants in Martian regolith amended with nutrients and organic matter, would reduce the need to carry growth medium from Earth, but Martian regolith contains perchlorate salts at concentrations toxic to most plants, requiring chemical treatment before use. Research into perchlorate-tolerant plant varieties and perchlorate-removing microorganisms is ongoing. The microbiome of a space habitat, the community of bacteria, fungi, and other microorganisms that inevitably colonize every surface and the bodies of every crew member, is an underappreciated component of the bioregenerative life support challenge. On Earth, the human microbiome is shaped by a complex, diverse environment of microorganisms encountered throughout daily life. In the closed, sterile environment of a spacecraft, the microbiome of the crew rapidly homogenizes. The crew members' microbiomes converge toward a single shared composition as they exchange microorganisms in the enclosed space. Research on the ISS microbiome has found that the station's surfaces harbor a surprisingly diverse and persistent community of organisms, including some that have evolved resistance to cleaning agents and antibiotics in response to the selection pressure of the heavily cleaned station environment. Managing the microbial ecology of a long-duration habitat, ensuring that beneficial microorganisms are maintained and harmful ones are controlled, is a life support challenge of growing recognized importance. The vision of a mature Mars food production system, one that can provide a significant fraction of the crew's caloric needs from locally grown food, is not merely a logistical efficiency. It is a psychological and cultural anchor. A crew that grows some of its own food has a relationship with its environment that is qualitatively different from a crew that depends entirely on supply deliveries from another world. The act of planting, tending, harvesting, of participating in the biological cycle of growth and consumption, is one of the most ancient and most deeply human activities. Bringing it to Mars is not a sentimental luxury. It is part of what it means to live somewhere, rather than merely to survive there. The difference between surviving on Mars and living on Mars may be, in part, measured in the smell of growing wheat and the taste of a fresh tomato 40 million miles from the nearest supermarket. As you drift towards sleep tonight, imagine that garden. Small, lit by artificial red and blue light in a module the size of a large bedroom, the plants in neat hydroponic trays, their roots white and clean in the nutrient solution, their leaves reaching for the LEDs above them with the same patient biological determination they would show in any field on Earth. The crew member tending them, checking the nutrient levels, training a vine onto its trellis, harvesting the outer leaves of a head of lettuce, doing something that human beings have been doing for 10,000 years on a world where it has never been done before. The closed-loop water cycling in a space garden is as elegant as it is necessary. Plants transpire, releasing water vapor through the microscopic pores in their leaves called stomata, and in a sealed habitat that water vapor is captured by the air conditioning system and condensed back into liquid water, which is returned to the hydroponic nutrient solution after treatment. The result is a nearly closed water cycle. The water the plants absorb from their roots passes through the plant, exits as vapor, condenses on the habitat walls or the dehumidifier coils, and returns to the reservoir. In a well-designed system, less than 5% of the water added to the plant growth system is lost per growing cycle. For a Mars base where every kilogram of water not brought from Earth represents significant mass savings, this efficiency is not a refinement. It is a survival feature. The caloric mathematics of Mars agriculture are instructive about both the potential and the limits of in-situ food production. A square meter of wheat under optimized LED lighting and CO2 enrichment can produce approximately 4 kilograms of grain per 60-day growing cycle, roughly 240 grams of grain per day per square meter, providing approximately 800 calories. A crew of 6 requiring approximately 2,400 calories per person per day needs a total of 14,400 calories daily. To provide all of those calories from wheat alone would require approximately 18 square meters of wheat growing area, a substantial but not impossible footprint within a large habitat module. In practice, a mixed crop system with higher calorie staples like sweet potato and soybean alongside lower calorie but nutritionally important leafy greens and legumes could provide a nutritionally complete diet from approximately 30 to 40 square meters of growing area. The growing area required to feed a crew of 6 entirely from in-situ agriculture fits comfortably within a single large habitat module. Not a distant aspiration, but an achievable near-term engineering target. The most consequential question that a Mars mission could answer, more consequential than any geological or atmospheric measurement, more significant than any engineering achievement, is whether Mars ever harbored life. The confirmation that life once existed on Mars, or that it exists there still, would be the most transformative scientific discovery in human history. It would mean that life is not unique to Earth, that it arose independently in at least 2 locations in the same solar system, and that by extension it is almost certainly common throughout the galaxy and the universe. It would mean that the universe is, at its most basic level, a living place, that biology is as fundamental a feature of the cosmos as chemistry or physics. It would answer, definitively and permanently, The question that every civilization in human history has asked in its own way: are we alone? The scientific case for Mars as a candidate for ancient life rests on two foundations. The first is the geological evidence for a wet, warm early Mars during the Noachian period, approximately 4.1 to 3.7 billion years ago, when liquid water was present on the surface in rivers, lakes, and possibly a northern ocean. The conditions of early Mars, by the best available reconstruction, were broadly similar to the conditions of early Earth during the same period, and on Earth, life appeared within a few 100 million years of the surface cooling sufficiently for liquid water to persist. If life arose on Earth in the first few 100 million years after liquid water became available, and Mars had liquid water for a similar duration, the same chemistry that produced life on Earth might have produced life on Mars. The second foundation is the discovery of organic molecules on Mars. The Curiosity rover has detected complex organic compounds, including thiophene, methylthiophanes, methanethiol, and dimethyl sulfide, in 3.5 billion-year-old mudstone at Gale Crater, preserved in the sedimentary rock against the harsh radiation environment. These molecules are not unambiguous biosignatures. They could have been produced abiotically, but they are the building blocks of biology, and their presence means the raw materials were available. The Perseverance rover, operating since February 2021 in the Jezero Crater Ancient Lake and River Delta, is the most sophisticated life detection instrument ever sent to Mars, although by design it does not perform definitive life detection on Mars itself. Instead, it collects and caches rock core samples in sealed titanium tubes, currently left on the Martian surface in a depot for eventual retrieval, that are intended for return to Earth laboratories by the Mars Sample Return Campaign, a joint NASA and European Space Agency project targeting sample return in the early 2030s. The rationale for sample return rather than in situ life detection is scientific rigor. The instrument's sophisticated enough to provide definitive evidence of past or present life, isotope ratio mass spectrometers, electron microscopes, advanced organic chemistry analyzers, are too large, too delicate, and too complex to operate robotically on the surface of Mars. The samples Perseverance is collecting will be analyzed in terrestrial laboratories by the full array of analytical chemistry tools that modern science has developed, under controlled conditions where ambiguous results can be reanalyzed and cross-checked until a definitive answer is established. The specific biosignatures that the Mars Sample Return Science team will search for are the same categories discussed in the context of exoplanet biosignature science: chemical disequilibrium, isotopic fractionation consistent with biological processing, morphological structures resembling microbial fossils, and the presence of complex organic molecules organized in patterns characteristic of biological synthesis. Carbon isotope ratios are particularly informative. Biological metabolism preferentially incorporates the lighter carbon-12 isotope over the heavier carbon-13, producing organic material systematically depleted in carbon-13 relative to the inorganic carbon in the surrounding rock. A carbon-13 depletion in organic matter from Martian sediment, coupled with other lines of evidence, would be a strong indication of biological origin. The same kind of carbon isotope signal is what geochemists used to detect the first evidence of life on Earth in rocks more than 3 billion years old. The possibility of extant, currently living, life on Mars is not dismissed by mainstream planetary science, though it is considered less probable than the possibility of ancient life. If life existed on early Mars and developed mechanisms for surviving in subsurface environments as the surface became cold and dry, it might have retreated progressively deeper into the crust as conditions deteriorated, following liquid water and geothermal heat downward over billions of years. The subsurface of Mars, below the permafrost layer, in deep aquifers or hydrothermal systems, could potentially harbor liquid water today, maintained by geothermal heat and depressed freezing point from dissolved salts. The MAVEN spacecraft has established that Mars's atmosphere is still losing gas to space today, implying ongoing geological and possibly volcanic activity that could sustain liquid water at depth. If liquid water exists in the Martian subsurface today, and if microbial life colonized those environments billions of years ago, the possibility that some lineage of that life persists cannot be ruled out. The search for extant life on Mars has a troubling complexity: contamination. Every spacecraft we have sent to Mars has carried Earth microorganisms on its surfaces, despite extensive sterilization protocols. The most heat-tolerant bacterial spores survive even the aggressive cleaning procedures used in spacecraft assembly. If we discover microbial life in the Martian subsurface, the first scientific question will be whether it is truly Martian or whether it is a descendant of Earth organisms inadvertently introduced by our rovers and landers. Distinguishing between truly indigenous Martian life and introduced terrestrial contamination requires that the Martian organisms have a different biochemistry, a different genetic code, different amino acids, different membrane lipids, from any Earth organism. If Mars life uses the same biochemistry as Earth life, determining whether it arose independently or was introduced by contamination becomes extraordinarily difficult. The planetary protection protocols governing Mars missions are designed to minimize this contamination problem, but they cannot eliminate it entirely, and the more we explore Mars, the more Earth organisms we potentially deposit there. The human Mars mission adds a new dimension to this contamination challenge that has no good solution within the current paradigm. Human beings shed enormous quantities of microorganisms, trillions of bacteria per day in skin flakes, respiratory droplets, and feces, and any human habitat on the Martian surface will be surrounded by a contamination halo of Earth biology within weeks of occupation. If life detection science is a priority of the human Mars mission, the crew must operate under strict protocols that prevent their biological contamination from reaching any site where Martian biosignatures might be present. This means that the most scientifically valuable Martian environments, the subsurface, the ancient hydrothermal systems, the sealed sedimentary layers that have been isolated from the surface for billions of years, are exactly the environments that human crews must be most careful not to contaminate. The tension between the scientific value of human presence and the scientific risk of human contamination is one of the deepest philosophical challenges of the Mars exploration program. There is a broader philosophical dimension to the search for Martian life that deserves acknowledgement. If we find evidence of life on Mars, ancient or extant, it will raise immediately the question of moral status. Does Martian microbial life have claims on the resources of the planet? Does the existence of a second independent origin of life in our solar system create obligations that constrain how we develop Mars? The Outer Space Treaty of 1967, the foundational international legal instrument governing space activities, prohibits harmful contamination of celestial bodies and requires consultation about potentially harmful activities, but its provisions are ambiguous about the moral status of extraterrestrial life that might be found. The discovery of life on Mars, if it comes, will require not just scientific interpretation but ethical reflection of a kind that humanity has never had to undertake before. Rest with the scale of that possibility. The Perseverance rover is on the surface of Mars right now, collecting its samples, caching them in their titanium tubes, driving slowly across the delta of a river that last flowed 3.5 billion years ago. The samples it is collecting may contain, in the chemistry of their ancient mudstones, the answer to the oldest question. They will lie on the Martian surface until the sample return mission arrives to collect them. And then they will make the long journey home, across the hundreds of millions of kilometers of space between the two worlds, carrying the question with them in sealed metal cylinders, patient and dark and cold, until the laboratories on Earth can finally read what they contain. The history of Mars and life has already produced one of the most dramatic and contested episodes in the history of science. In August 1996, a team led by David McKay at NASA's Johnson Space Center published a paper in Science announcing that they had found evidence of ancient Martian life in a meteorite called ALH-84001, a 4.5-kilogram piece of Martian rock that had been blasted off the Martian surface by a large impact approximately 16 million years ago, drifted through interplanetary space, fell to Earth in Antarctica approximately 13,000 years ago, and was collected from the Allen Hills ice field in 1984. The evidence McKay's team presented included carbonate globules of the type produced by some bacteria on Earth, polycyclic aromatic hydrocarbons of possible biological origin, and, most dramatically, tiny ovoid and tubular structures that the team argued could be fossilized nanobacteria. The announcement, made at a press conference attended by President Clinton, generated worldwide excitement. NASA estimated it was the most significant scientific announcement in human history. The excitement was not sustained. Over the following years, alternative explanations for each line of evidence in ALH-84001 were proposed and, in most cases, found at least as plausible as the biological hypothesis. The carbonate globules could have formed abiotically at high temperatures. The PAHs were consistent with contamination from terrestrial sources during the meteorite's 13,000 years in Antarctica. The putative fossil structures were far smaller than any known bacteria, smaller, many microbiologists argued, than any cell could physically be and still contain the molecular machinery required for life. The scientific consensus today is that ALH-84001 does not provide convincing evidence of ancient Martian life, though the debate has never been entirely closed. What ALH-84001 did do was establish, for the first time, that the question of Martian life was a legitimate scientific question that could be addressed with physical evidence, and it mobilized the scientific and political will that eventually produced the Mars exploration program that culminated in Perseverance and the Mars Sample Return Campaign. Of all the challenges of long-duration space exploration, the radiation, the microgravity, the technical complexity, the logistical difficulty, the one that is simultaneously the most human and the most underappreciated is the psychological challenge. The engineering of a rocket can be tested, iterated, and improved based on measurable performance metrics. The psychology of a small group of people confined together in an isolated, dangerous environment for 18 months, completely cut off from the social world that shaped them, bearing the weight of a mission whose success or failure will have historical consequences. This cannot be fully tested in advance, fully engineered, or fully controlled. It involves human beings, with all their complexity and unpredictability, operating under conditions of stress that no Earth analog can perfectly replicate. The research base of space psychology draws on several decades of analog environment studies. The most rigorous are the Antarctic winter-over studies, in which small crews of 6 to 13 people spend 9 to 11 months in isolated research stations during the polar winter, with no possibility of evacuation and limited communication with the outside world. The psychological effects of Antarctic winter-over have been extensively documented, a characteristic pattern called the third quarter phenomenon, in which morale and cognitive performance decline most sharply in the third quarter of the winter, when the initial excitement of the mission has worn off but the end is not yet in sight, has been observed consistently across Antarctic stations, submarine deployments, and isolated habitat simulations. Interpersonal conflict between crew members follows predictable trajectories. Minor irritants escalate through inattention. Communication patterns shift as subgroup alliances form. Authority relationships become strained as mission commanders and their crews navigate the tension between hierarchical decision-making and the democratic norms that highly educated, independent-minded professionals typically expect. The specific stress structure of a Mars mission has several features that distinguish it from any Earth analog. The most unique is the progressive communication delay. At the beginning of a Mars mission, when Earth and Mars are relatively close, the communication delay is a few minutes, still long enough to prevent real-time conversation, but short enough for back-and-forth exchanges within an hour. As the mission progresses and the planets move to opposite sides of the Sun, the delay grows to over 20 minutes one way, making real-time conversation impossible and replacing it with asynchronous message exchange, the space equivalent of writing letters. The crew's relationship with the Earth-based support teams, their families, and the broader human world will evolve from something resembling a phone call to something resembling 19th century correspondence, long, composed, deliberately written messages that arrive hours apart, across distances that would take years to cross in person. This progressive isolation has been studied in the Mars 500 simulation in Moscow, where 6 volunteers spent 520 days in a mock Mars mission habitat with artificially imposed communication delays that increased over the course of the simulation. The results showed that the crew adapted to the delays and maintained functional communication with the ground team throughout, but that the quality and frequency of personal communications with family and friends declined substantially as the delay increased. The crew gradually shifted from treating Earth-based support as an active partner in decision-making to treating it as a source of information and historical records, available for consultation but not for real-time guidance. This shift in the crew-ground relationship is not pathological. It is, in a sense, the appropriate adaptation to the genuine operational reality of Mars distance. But it requires psychological preparation, because it means that the crew must be capable of genuine autonomous authority, making decisions that would normally involve extensive consultation with Earth-based experts, in a compressed timeline that the communication delay imposes. The composition and dynamics of the crew are among the most consequential design decisions in the entire Mars mission architecture. A crew of 6 people will spend 3 years together, from the intensive pre-flight training that builds the team, through the long transit, through the surface stay, through the return, in closer proximity and higher interdependence than most families achieve in a lifetime. The selection of crew members for psychological compatibility, for resilience under stress, for conflict resolution skills, and for the specific combination of personality traits that allows functional teamwork in isolated environments has been studied intensively by the space psychology community. The research consistently finds that a crew's success in long-duration missions is less dependent on the individual competence of its members than on the quality of their interpersonal relationships, their ability to communicate honestly, manage conflict constructively, maintain respect under stress, and support each other's well-being over a duration that tests every social skill they possess. The role of the mission commander in a Mars crew deserves specific attention. In the early history of human spaceflight, the commander was primarily a pilot, the person responsible for flying the spacecraft safely. In a long-duration surface mission, the commander's role shifts fundamentally toward team leadership, managing interpersonal dynamics, monitoring crew morale and health, making the autonomous operational decisions that the communication delay makes impossible to defer to Earth, and maintaining the crew's motivation and sense of purpose over a duration long enough for even the most committed person to experience periods of doubt, fatigue, and discouragement. This is a leadership challenge more analogous to the command of a long naval voyage or a polar expedition than to the command of a short spaceflight, and the selection and training of Mars mission commanders reflects that understanding. The return journey from Mars, 9 months of transit after approximately 500 days on the surface, presents a distinct psychological challenge that is sometimes underestimated in mission planning. The crew will be leaving a world they have come to know, with its specific gravity and weather and geology, and perhaps with attachments to the base they built and the discoveries they made. They will be returning to a world that has continued without them for 3 years. Families have changed, careers have evolved, the world of 2000 and whatever year has moved on while they were away. The psychological adjustment to return to Earth's full gravity after nearly 2 years of reduced gravity, to the complexity and noise of social life after years of the sparse social world of a 6-person crew, to the media attention and historical significance that will attach to them as the first humans on Mars, is its own transition that requires support and preparation. The first Mars crew will not simply return to Earth. They will return to a life that has changed around an absence they cannot fully explain to people who were not there. The inner frontier of a Mars mission, the frontier of human psychology under extreme conditions, is, in a sense, the final and most fundamental challenge. Every external challenge of Mars exploration can be addressed with engineering, better rockets, better habitats, better radiation shielding, better ISRU systems. The psychological challenges are addressed with something more complex and less predictable, with people, with training, with the social technologies of communication and conflict resolution and leadership and mutual support that human beings have been developing, imperfectly, throughout their entire history. The people who go to Mars will carry with them not just their technical expertise but the entire weight of human social evolution, all the adaptive and maladaptive patterns of behavior that a few million years of living in small groups under pressure has produced. They will need the best of those patterns. On the best days, they will find them. And on the worst days, they will find something else, the resilience and the creativity and the sheer stubbornness of a species that has survived every previous frontier it has encountered, and refuses, in its deep nature, to stop. Sleep now. Somewhere in the planning rooms and training facilities and simulation chambers where the Mars mission is being prepared, people are working on exactly this, on the psychology, on the team dynamics, on the communication protocols and the conflict resolution frameworks and the crew selection criteria that will determine whether the first humans on Mars thrive or merely survive. It is careful, patient, unglamorous work. It is as important as any rocket engine or habitat module. And the people doing it understand that the hardest part of going to Mars is not the distance. It is being human, for 3 years, in the most extraordinary and demanding circumstances our species has yet encountered. Behavioral health monitoring technologies are advancing rapidly alongside the mission architecture. Passive monitoring systems, sensors embedded in the habitat that track sleep patterns from mattress movement, activity levels from wearable devices, voice characteristics that may indicate stress or depression, communication frequency and tone in crew messages, can provide continuous, low-intrusiveness data on crew psychological state without requiring the crew to complete formal psychological assessments that they might be reluctant to engage with honestly if they feel their responses could affect their mission standing. An AI-based behavioral health monitoring system that can alert the crew medical officer to early warning signs of depression, interpersonal conflict escalation, or cognitive decline, before the crew member or their crewmates have consciously registered the change, represents a new category of mission support tool that is being actively developed by the space medicine community. The question of who gets to go to Mars, the selection criteria, the equity, the cultural and national composition of the first crews, is one that involves values as much as technical requirements. The first humans to walk on Mars will be among the most consequential historical figures of the 21st century, and the decisions about who they are will reflect the values and priorities of the civilization that sends them. The Artemis program's explicit commitment to crew diversity, the first woman and the first person of color on the Moon, represents a deliberate statement about who the future of space exploration belongs to. Extending that commitment to the first Mars crews will require sustained effort against the institutional inertias that have historically constrained who participates in elite technical programs. The people who go to Mars will shape, by their example and their choices and their stories, the culture of the interplanetary civilization that follows them. That is not a trivial responsibility, and it is one that begins with the selection process, years before launch. There is a thought experiment that sits at the far end of the trajectory we have been tracing, beyond the first landing, beyond the permanent base, beyond the first generation of children born under Martian gravity. The thought experiment asks, what if we did not merely survive on Mars, but changed it? What if, over centuries or millennia, humanity applied its technological ingenuity not just to the engineering of habitats within the Martian environment but to the engineering of the Martian environment itself, warming the planet, thickening its atmosphere, filling its ancient riverbeds with liquid water, and transforming a world that today cannot support unprotected human life into one where a person could eventually step outside without a spacesuit. This is terraforming, the deliberate modification of a planet's climate, atmosphere, and surface conditions to make them more Earth-like. And it is, depending on who you ask, either the most audacious long-term project the human species could undertake, a scientific impossibility given current understanding of Martian atmosphere, or a profound ethical mistake that should never be attempted regardless of technical feasibility. The scientific foundation for Mars terraforming rests on Mars's own history. Mars was once warmer and wetter than it is today. Its ancient riverbeds and lake basins and possible northern ocean are the geological record of a planet where the conditions for life, as we understand them, once existed. The planet lost those conditions not because of any fundamental physical law that prevents a warm, wet Mars from existing, but because of a specific sequence of events, the loss of the global magnetic field, possibly caused by the cessation of core convection as the planet's smaller iron core cooled. The loss of the magnetosphere removed the protection against solar wind stripping of the atmosphere. The light hydrogen atoms in the upper atmosphere were gradually lost to space, reducing the water content. The carbon dioxide was progressively locked into carbonate minerals in polar ice. Mars today is cold and dry because of a process, not an inevitability. In principle, that process could be reversed, or at least its end state modified. The most discussed pathway to Mars terraforming begins with warming the planet. The current mean surface temperature of Mars is approximately -60 degrees Celsius, far below the freezing point of water. Raising this temperature by 40 to 60 degrees Celsius would, in most scenarios, be sufficient to allow liquid water to exist on the Martian surface at least seasonally, and would trigger the sublimation of the South Polar carbon dioxide ice cap, releasing additional CO2 into the atmosphere that would enhance the greenhouse effect and drive further warming in a positive feedback. Several mechanisms for initiating this warming have been proposed. Deploying large orbital mirrors, thin reflective films with areas of hundreds of square kilometers, positioned in solar orbit to redirect additional sunlight onto the Martian poles, could initiate polar cap sublimation within decades. Introducing powerful greenhouse gases, specifically engineered fluorinated compounds like perfluorocarbons, which are thousands of times more potent greenhouse agents than CO2 and are not present in the Martian atmosphere, at concentrations achievable by industrial production, could warm the surface by tens of degrees over centuries. The carbon dioxide locked in the Martian regolith and polar caps represents a potentially massive reservoir that, if fully released, could thicken the atmosphere substantially. Studies of the Martian carbon inventory suggest that the total amount of CO2 that could be mobilized from the poles and regolith by warming might be enough to raise atmospheric pressure to perhaps 30 to 50 millibars, approximately 3 to 5% of Earth's sea level pressure, and roughly 3 to 5 times the current Martian atmospheric pressure. This is significant but still insufficient for unprotected human respiration, which requires an atmosphere with adequate partial pressure of oxygen at roughly 200 millibars. The CO2 mobilization pathway brings Mars to a stage where liquid water is possible and the temperature is hospitable, but it does not produce breathable air. The production of breathable air, or at minimum, sufficient oxygen partial pressure for humans to breathe without closed-circuit systems, requires either the biological production of oxygen by photosynthetic organisms over centuries or millennia, or industrial oxygen production at planetary scale, which is almost certainly beyond any foreseeable technology. The biological pathway to terraforming, seeding Mars with photosynthetic microorganisms engineered to survive in the early terraforming environment, cold-tolerant and radiation-resistant, able to begin producing oxygen from CO2, is the scenario that most serious scientific treatments of terraforming converge on as the primary oxygen production mechanism. On Earth, the Great Oxidation Event, when photosynthetic cyanobacteria transformed Earth's anoxic early atmosphere into the oxygen-rich atmosphere that enabled complex animal life, took approximately 300 million years. On Mars, with its lower gravity and the possibility of engineering organisms specifically for the purpose, the timescale might be compressible to centuries or millennia, though even the most optimistic scenarios envision a process taking on the order of thousands to tens of thousands of years to produce a breathable atmosphere. The technological constraints on terraforming are serious but not obviously insurmountable over very long timescales. The ethical constraints are harder. If Mars harbors extant microbial life, in its subsurface, in its hydrothermal systems, in any niche where liquid water persists, then terraforming would constitute the largest act of biological genocide in human history, the deliberate extermination of an entire alien biosphere to convert the planet to human use. The same discovery of Martian life that would be the most transformative scientific event in human history would also, if we proceed with terraforming, make us responsible for that life's extinction. Most planetary scientists and ethicists who have written on the subject argue that the question of terraforming cannot be meaningfully separated from the question of life. If Mars is sterile, the ethical objections to terraforming are weak. If Mars harbors any form of life, the ethical objections become overwhelming. The physicist and philosopher Paul Davies has argued that the discovery of life on Mars would be, in a sense, the worst possible news for the terraforming project. It would confirm both that Mars once harbored the conditions for life and that we cannot in good conscience modify those conditions away. Robert Zubrin, the founder of the Mars Society and one of the most passionate advocates for human Mars exploration, takes the opposite view, that if Mars life exists but is descended from Earth life, transported to Mars by meteorite, it has no independent moral status that trumps the project of making Mars habitable for a technological civilization. The debate is not resolved, and it cannot be resolved until the question of Martian life itself is resolved, which is one of the reasons why the search for life on Mars is the most urgent scientific priority of the planetary exploration program. Assuming Mars is sterile, the scenario that allows terraforming to proceed without the ethical catastrophe of extinguishing a second biosphere, the engineering challenge remains breathtaking. The total energy required to warm Mars, release its CO2 reserves, and maintain the resulting atmosphere against ongoing solar wind loss, Mars still lacks a magnetic field, over thousands of years as many orders of magnitude beyond any energy source available today, or any energy source that can be reasonably projected for the coming century. Some proposals involve restarting the Martian core's convection to regenerate a magnetic field, an engineering project of almost incomprehensible scale. Others involve constructing an artificial magnetic shield, positioned at the Mars L1 Lagrange point between Mars and the Sun, that would deflect the solar wind before it reaches the Martian atmosphere, a proposal taken seriously enough to have been published by NASA scientists, who estimate that such a shield could allow the Martian atmosphere to gradually thicken as CO2 outgasses from the regolith, over a period of centuries. Terraforming is not a project for the generation that lands on Mars, or the generation that builds the first base, or perhaps the generation that establishes the first city. It is a project for a civilization, a multi-generational commitment to a transformation of planetary scale, requiring not just technical capability but a form of political and cultural continuity that human civilization has never before sustained over the timescales required. The Roman Empire lasted 500 years. The most persistent human institutions, certain religious traditions, certain languages, certain agricultural practices, have persisted for a few thousand. Terraforming requires persistence and purposeful action over timescales 10 times longer than the longest-lived human institutions. Whether the civilizations that inhabit Mars in the distant future will still want to terraform it, or whether they will, as some science fiction writers have imagined, come to love the planet as it is and resist its transformation, is a question that belongs to futures so distant that they are more philosophy than planning. Terraforming is not a project for the generation that lands on Mars, or the generation that builds the first base, or perhaps the generation that establishes the first city. It is a project for a civilization, a multi-generational commitment to a transformation of planetary scale, requiring not just technical capability but a form of political and cultural continuity that human civilization has never before sustained over the timescales required. The Roman Empire lasted 500 years. The most persistent human institutions, certain religious traditions, certain languages, certain agricultural practices, have persisted for a few thousand. Terraforming requires persistence and purposeful action over timescales 10 times longer than the longest-lived human institutions. Whether the civilizations that inhabit Mars in the distant future will still want to terraform it, or whether they will, as some science fiction writers have imagined, come to love the planet as it is and resist its transformation, is a question that belongs to futures so distant that they are more philosophy than planning. The specific proposal for an artificial magnetic shield at the Mars L1 Lagrange point, the gravitationally stable point between Mars and the Sun, approximately 1 million kilometers sunward of Mars, was published in 2017 by Jim Green and colleagues at NASA's Planetary Science Division. The proposal envisions a large superconducting magnet or a plasma torus generating a magnetic dipole field strong enough to deflect the solar wind before it reaches the Martian upper atmosphere. Without solar wind stripping, the Martian atmosphere would gradually thicken as CO2 outgases from the polar caps and the regolith, and the water lost to space over billions of years would, at least partially, be retained as the atmosphere is restored. Computer simulations of the scenario suggest that within a few decades of deploying such a shield, Mars could have a mean surface temperature 2 to 3 degrees warmer, and within a century to a few centuries, liquid water could become stable on the surface at lower latitudes during summer. The atmospheric pressure would still be far below Earth's, and the atmosphere would be primarily CO2 rather than the nitrogen-oxygen mixture breathable by humans, but the process of transformation would be underway. The concept of paraterraforming, creating enclosed human habitable environments on the Martian surface rather than transforming the entire planetary atmosphere, offers an intermediate path between the present state and full terraforming that is technically much more accessible on relevant human timescales. Rather than changing the entire planetary atmosphere, paraterraforming would involve constructing large pressurized enclosures, domes or covered craters, containing Earth-like atmospheres and ecosystems. The scale of such structures could grow progressively, from the initial small habitat modules of the first base, to larger domed settlements covering several square kilometers, to eventually enclosed valleys and crater basins covering hundreds or thousands of square kilometers. Paraterraforming could, in principle, create large areas of habitable Martian surface within centuries rather than millennia, without requiring the transformation of the planetary atmosphere as a whole. The two approaches are not mutually exclusive. Paraterraforming could provide habitable environments on shorter timescales while the slower process of atmospheric terraforming proceeds in parallel. The philosophical debate about whether terraforming is desirable, independent of whether it is feasible, is one of the more interesting ethical discussions in contemporary philosophy of science. The deep ecology argument against terraforming holds that Mars, even in its current sterile and apparently lifeless state, has intrinsic value as a product of billions of years of natural geological and atmospheric processes, a value that does not depend on its being inhabited or useful to humans, and that would be violated by deliberate transformation. This argument treats planets as having a kind of wild integrity analogous to the wild integrity that deep ecologists attribute to Earth's natural ecosystems. The anthropocentric counterargument holds that intrinsic value in natural systems derives from the presence of life and conscious experience, and that a sterile Mars has no more intrinsic value than a pile of sand, that its transformation in service of life and consciousness is, if anything, an increase in value rather than a decrease. Neither argument is obviously correct, and the debate reveals fundamental disagreements about the sources of moral value that have not been resolved in the more familiar context of environmental ethics on Earth. The science fiction tradition has engaged with the ethics and the practice of terraforming more deeply and more imaginatively than any scientific or philosophical literature, and the best of that literature deserves acknowledgement. Kim Stanley Robinson's Mars trilogy, Red Mars, Green Mars, Blue Mars, published between 1992 and 1996, remains the most comprehensive and scientifically grounded fictional treatment of Mars terraforming ever written. The trilogy follows the first 100 settlers on Mars and their descendants over 2 centuries of terraforming, exploring the political, social, ecological, and philosophical dimensions of the project with a depth that has genuinely influenced the thinking of planetary scientists and space policy analysts. Robinson's work introduced the concept of the Reds, those who wish to preserve Mars as a wild, untransformed planet, against the Greens who wish to terraform it, and the Blues who seek a middle path. Those categories now appear in real policy discussions about the future of Mars development, borrowed from fiction because they capture genuine ethical tensions more precisely than any non-fiction framework has managed. The practical timeline for even the first steps of Mars terraforming, initiating the warming phase, deploying greenhouse gas production infrastructure, beginning the biological seeding, is measured in centuries from the present, and the technology required does not yet exist. This does not make it a meaningless discussion. The decisions made in the first decades of human presence on Mars, about where to land, what to study, what to disturb and what to preserve, how aggressively to develop ISRU capabilities versus how carefully to contain human biological contamination of the Martian environment, will foreclose or preserve options for terraforming on longer timescales. The first Mars settlers will make decisions whose consequences will extend for thousands of years. The environmental philosophy and the ethical frameworks they bring to those decisions will matter enormously. Building those frameworks now, before the first human sets foot on Mars, before the first irreversible choice is made, is not premature. It is precisely the right time. The economic dimension of terraforming is rarely discussed but is in some respects the most decisive. Terraforming a planet requires sustained investment of resources, energy, materials, technological capability, human attention, over timescales that exceed the economic planning horizon of any existing institution by orders of magnitude. No corporation plans beyond a few decades. No government reliably commits resources beyond a few political cycles. No international institution has a demonstrated ability to maintain a focused program over centuries. The governance structure that could sustain a terraforming project over 1,000 years does not currently exist and may require forms of institutional innovation that have no precedent in human history. Whether such institutions can be built, whether a civilization with sufficient continuity of purpose to undertake and complete a 1,000-year planetary engineering project is achievable, is perhaps the deepest question that terraforming raises, and it is a question about human institutions rather than about planetary science. As you settle towards sleep, let the scale of the terraforming question become restful rather than overwhelming. It is a question for centuries, for generations of people who do not yet exist, for civilizations that will have access to knowledge and technology and wisdom that we cannot currently imagine. The question is not ours to answer. Our task, the task of the people alive in the 21st century, is simply to get there. To land on Mars. To build the first base. To determine whether Mars harbors life. To make a start. Everything that comes after that start, the para-terraforming and the full terraforming and the politics of an interplanetary civilization and the moral philosophy of planetary transformation, follows from that beginning. We need only begin. And yet the dream of terraforming is not merely fantasy. It is the logical extension of the same impulse that builds habitats, grows food, produces oxygen from rock, the impulse to make a place habitable, to extend the range of conditions under which human life is possible, to refuse the universe's default settings when they are incompatible with human flourishing. That impulse is very old. It is what drove the first humans to build shelters against the cold, to irrigate fields against the drought, to heat homes against the winter. Terraforming is that impulse applied at planetary scale, over geological time. Whether it is wise, whether it is ethical, whether it is something any civilization should actually attempt, these are questions that the people who will be in a position to answer them will face in a future we cannot clearly see. The best we can do from here is understand the science, engage honestly with the ethics, and resist the temptation to make their decision for them. We have traveled a long way in this series. From the Apollo blueprints and the 50-year pause to the architecture of Artemis and the first steps back to the moon. From the 7 minutes of terror above the Martian surface to the slow construction of a base from ice and regolith and 3D printed sulfur concrete. From the bone loss and the bioluminescent gardens and the communication delays growing to 20 minutes round trip to the oldest question of all, waiting in a sealed titanium tube on the floor of an ancient Martian river delta. We have visited the technical and the human and the philosophical dimensions of what it means to extend human civilization beyond the single planet where it began. And now, in this final episode, we take the longest view, not the first mission, not the first base, but the arc of a civilization becoming interplanetary, the decades and centuries of what might come after the first footprint on Mars. The trajectory from first landing to permanent settlement to something that could genuinely be called a Martian civilization follows a logic that has precedence in terrestrial exploration history, though the distances and difficulties are incomparably greater. The initial expeditions, analogous to the first voyages to Antarctica, or the first European crossings of the Atlantic, establish proof of concept and gather scientific data. The permanent research stations that follow, analogous to Antarctic research bases, or the early European settlements in the Americas, developed the operational knowledge and the physical infrastructure that makes sustained presence possible. The growth of those stations into something with an economy, a culture, and a population capable of self-reproduction, the point at which the settlement no longer depends entirely on supply from its origin world, is the transition from outpost to colony, and it is the transition that most fundamentally changes the nature of the human presence on another world. The question of when a Mars settlement could become self-sustaining, capable of supporting itself without continuous supply from Earth, is primarily an engineering and economic question, but it has profound philosophical implications. Self-sufficiency requires a population large enough to maintain the full range of technical expertise needed to operate and repair all the critical systems of the settlement: the life support, the power generation, the food production, the manufacturing capabilities, the medical capacity. Current estimates suggest that a self-sustaining Mars settlement would require a population of somewhere between 1,000 and 10,000 people, depending on the degree of automation and the efficiency of the supply chain. Below that threshold, the settlement is an extension of Earth's civilization, dependent on Earth for critical supplies and expertise. Above it, the settlement has the potential to be something genuinely new, a human civilization with its own resources, its own economy, its own culture, and, eventually, its own interests that may not perfectly align with Earth's. The economic foundation of an interplanetary civilization is one of the deepest uncertainties in long-range space planning. What does Mars produce that Earth wants? The most commonly discussed candidates are intellectual property, scientific discoveries, technological innovations made in the Mars environment, and rare materials, though the cost of transporting physical goods between planets is so high that only extremely high value per unit mass materials could be economically justified. Some economists have argued that the most valuable export of a Mars civilization would be the development of closed-loop life support, ISRU, and manufacturing technologies that are economically valuable on Earth for terrestrial applications, technologies developed under the extreme efficiency requirements of a planet where everything is scarce, which then diffuse back to Earth where they reduce the resource intensity of production. Others have argued that the economic model for Mars will be fundamentally different from any Earth precedent, that a civilization operating at the frontier of survival, where innovation is literally a matter of life and death, will produce a rate of technological development analogous to the accelerated innovation of wartime, creating economic value through the technologies it develops rather than through the goods it produces. The social and political structure of a Mars settlement is a subject of intense speculation and genuine importance. The early settlement will necessarily be highly authoritarian in one specific sense: the life support systems are not optional, the safety protocols are not advisory, and the decisions that could kill the entire settlement cannot be subject to endless democratic deliberation. A habitat breach requires immediate action, not a committee vote. In the early years, the settlement's governance will look more like a ship's crew or an Antarctic research station than a democracy, hierarchical, mission-oriented, with clear lines of authority for emergency decision-making. But as the population grows and the existential urgency of the early phase gives way to something more like ordinary life, the governance question becomes genuinely open. Will Mars develop democratic institutions? Will the distance from Earth's legal and political structures allow it to develop entirely new forms of governance? Will the specific experiences of the Martian environment, the absolute dependence on collective action for survival, the necessity of long-term thinking in a world where every resource must be managed carefully, the shared identity of a population that chose to be somewhere extraordinarily difficult, produce a political culture distinctly different from Earth's. The question of who goes to Mars, not just in the first missions but in the long process of building a civilization, is one that involves equity and justice in ways that the space policy community is only beginning to seriously engage with. The history of exploration and colonization on Earth is heavily burdened with episodes of dispossession, exploitation, and cultural destruction that cast long shadows over the present. The question of how to ensure that the expansion into space does not replicate those patterns, that it does not become the project of a wealthy few, that it does not import the inequalities of Earth into a new context, that it provides genuine opportunity for participation across the full range of human diversity, is a question of values, not just logistics. The Artemis Accords and their emphasis on inclusive participation, the explicit commitment to crew diversity in the Artemis program, the growing engagement of the space policy community with questions of equity and access, these are early steps in a conversation that will need to continue and deepen as the scale of the human space program grows. There is a deeper question underneath the practical and political questions. Why does it matter? Why should humanity invest the enormous resources and accept the significant risks of becoming a multi-planetary species? The most common answer, the existential insurance argument, that spreading across multiple planets reduces the risk of human extinction from any single planetary catastrophe, is compelling as far as it goes. But it is, in a sense, the minimum justification. We should go to other worlds because we might die if we don't. The more interesting and more honest answer is that the expansion into space is an expression of something fundamental about what the human species is. We are the species that crossed the open ocean in outrigger canoes without knowing what was on the other side. We are the species that walked out of Africa and across every continent on Earth, adapting to environments far removed from the savanna where we evolved. We are the species that has spent the entirety of its existence moving toward the horizon and then looking for the next horizon beyond it. Mars is the next horizon. The moons of the outer solar system are the horizon after that. The stars are further still, and the distances involved are almost incomprehensible, but they too are there. And we are the kind of species that will eventually ask the question of whether they can be crossed. The philosopher and cosmologist Carl Sagan argued that the expansion into space was not merely optional for the long-term survival of humanity but morally obligatory, a responsibility to the continuity of consciousness and culture in a universe that, as far as we know, produced those things only once, on one small planet, after 4 billion years of biological evolution. The loss of everything that human civilization has created, its art and science and music and literature and love and ethical reflection, in a single planetary catastrophe, when a second planet was accessible and could have been settled, would be, in Sagan's view, a cosmic tragedy of the highest order. Not just a tragedy for the humans who would die, but a tragedy for the universe, which would lose its only known capacity for self-understanding. Whether one accepts that frame or not, it captures something true about the stakes. The long-term survival of everything that makes human existence meaningful depends, in the fullness of geological and cosmic time, on not remaining confined to a single world. The first humans on Mars, whoever they are, whenever they arrive, from whatever nation or agency or private company that sends them, will carry with them the entire weight and richness of the human story up to that point. Every painting, every symphony, Every mathematical proof, every story told around every fire since the first fire, every act of love and courage and curiosity and stubbornness that has characterized this extraordinary and improbable species, all of it will be embodied in the people who first stand on the Martian surface and look back at the sky to find a small blue dot that is everything humanity has ever known or loved or built. They will be, in that moment, the furthest point of the human story from its beginning. And the most important thing about that moment will not be what they see when they look at the Martian landscape. It will be what they see when they look back at the dot. And what they choose to do next. Tonight, as you drift towards sleep on the single world we currently inhabit, the moon is rising somewhere above the horizon, its gray surface as patient and unchanged as it has always been. The rovers on Mars are trundling across their ancient valley floors, their instruments humming, their cameras recording. The engineers in their offices and laboratories are solving the next problem on the long list of problems between here and Mars. The astronauts in their training facilities are preparing their minds and bodies for the environments they will one day encounter. The scientists studying the samples and the telemetry in the orbital imagery are building, incrementally, the understanding of other worlds that will make it possible for humans to live there. And somewhere in all of that work, in all of those people, in all of those hours of careful and patient effort, the next chapter of the human story is being written. We are going back to the moon. We are going to Mars. Not because it is easy, it is not easy, and anyone who tells you otherwise is simplifying. But because the kind of species we are does not stop at the edge of the known, and the universe has left the next world close enough that we can reach it, and we are finally, again, after the long pause, reaching. The first steps are being taken right now. The first habitats are being designed. The first people who will land on Mars are, most likely, alive somewhere on Earth tonight, perhaps already selected in training, perhaps still children, perhaps not yet born. They are real. The world they will stand on is real. The distance between here and there is real and crossable. And the story that will be told about this era, of the return to the moon and the first footprint on Mars, will be one of the great chapters in the long and improbable history of a species that refused, generation after generation, to stop looking up. The relationship between Earth and a growing Mars settlement will evolve in ways that are genuinely difficult to predict, because it will be shaped by economic, political, and cultural forces that do not yet exist. The early relationship will be one of profound dependency. The settlement depends on Earth for critical supplies, for technical expertise, for the communication and navigation infrastructure that keeps it connected to the larger human world. Over decades, as the settlement's ISRU capabilities mature and its population grows, the dependency will decrease, and with it, the political relationship will shift. Earth-Mars relations in the 22nd century may look something like the relationship between metropolitan Europe and its colonial settlements in the 17th century, a relationship structured by economic interest, political authority, and cultural connection that gradually gives way, through processes that cannot be entirely anticipated in advance, to something more like the relationship between independent nations that share a common origin. The American Revolution, in this analogy, is not an inevitability. Some Mars settlers might prefer continued close integration with Earth, but it is a possibility that grows more likely as the settlement becomes more capable of self-determination. The speed of light communication delay between Earth and Mars imposes a constraint on political and economic integration that has no terrestrial analogy. When a message takes 20 minutes to cross a distance, and a response takes 20 minutes to return, the real-time coordination that characterizes modern economic and political systems on Earth is impossible. Financial markets operate on millisecond timescales. Democratic deliberation requires real-time communication among participants. A Mars civilization operating under a 40-minute round-trip communication delay will necessarily develop different economic institutions, different political processes, and different cultural rhythms than Earth, not because it chooses to be different, but because the physics of its situation make the Earth's institutions unworkable at that distance. The development of those new institutions, new forms of economic exchange calibrated to light speed delays, new democratic processes that function without real-time communication, new cultural forms adapted to a world where news from home is always 40 minutes old, will be one of the most interesting social and intellectual challenges of the interplanetary era. The Fermi paradox, the question of why, if intelligence is common in the galaxy, we have found no evidence of it, has a bearing on the long-term project of human expansion into space that is worth acknowledging. One resolution of the Fermi paradox, known as the Great Filter, suggests that at some point in the development of technological civilizations, the vast majority fail, that there is some obstacle, biological, social, technological, or political, that most civilizations do not survive. If the Great Filter lies in the past, if the evolution of complex multicellular life, or the development of intelligence, or some other improbable step in our history is the filter, then we may be rare and lucky, and the path to becoming an interplanetary civilization is open. If the Great Filter lies in the future, if most civilizations that reach our current level of technological capability subsequently destroy themselves, through nuclear war, climate catastrophe, engineered pandemic, or some other mechanism, then the Fermi paradox is a warning rather than a puzzle. Becoming a multi-planetary species is, in this reading, not a long-term aspiration but an urgent defense against the specific vulnerability that the Great Filter identifies, the fragility of a civilization confined to a single world. The astronomer Nick Bostrom has argued, somewhat grimly, that the discovery of life on Mars would actually be bad news in this context, because it would increase the probability that the Great Filter lies ahead rather than behind, that the evolution of complex life is not rare, and therefore the rarity of intelligent civilizations in the galaxy is explained by something that destroys them later. This is not a commonly shared view, but it illustrates the depth of the connection between the search for extraterrestrial life and the question of humanity's long-term future. The cultural legacy of the Apollo program, the images, the stories, the collective memory of a generation, demonstrates that human space exploration produces cultural effects that outlast the missions themselves and influence the civilization that follows them for generations. The Earthrise photograph changed how humanity thought about its home planet. The pale blue dot image, taken by Voyager 1 from beyond the orbit of Neptune, produced a philosophical reflection by Carl Sagan that has been read by tens of millions of people and continues to circulate as one of the most powerful expressions of what space exploration means for human self-understanding. The images that future Artemis and Mars crews will take, of Earth as a brilliant in the Martian sky, of Olympus Mons from the ground, of the first human habitat on another world lit against the black space, will produce their own cultural resonances, their own shifts in collective self-understanding that we cannot fully anticipate. History suggests they will be profound. History suggests they will endure. The cultural legacy of the Apollo program, the images, the stories, the collective memory of a generation, demonstrates that human space exploration produces cultural effects that outlast the missions themselves and influence the civilization that follows them for generations. The Earthrise photograph changed how humanity thought about its home planet. The pale blue dot image, taken by Voyager 1 from beyond the orbit of Neptune, produced a philosophical reflection by Carl Sagan that has been read by tens of millions of people and continues to circulate as one of the most powerful expressions of what space exploration means for human self-understanding. The images that future Artemis and Mars crews will take, of Earth as a brilliant in the Martian sky, of Olympus Mons from the ground, of the first human habitat on another world lit against the black space, will produce their own cultural resonances, their own shifts in collective self-understanding that we cannot fully anticipate. History suggests they will be profound. History suggests they will endure. There is also a scientific dimension to the long future that extends far beyond what any single mission or program can achieve. The systematic exploration of the solar system, all of it, not just the Moon and Mars but the asteroid belt, the outer planets and their moons, the Kuiper belt objects, the boundary of the heliosphere, represents a scientific program of centuries that will transform our understanding of planetary formation, the distribution of water and organics in the early solar system, the conditions under which life can arise and persist, and the geological and atmospheric history of every world within reach. The human and robotic elements of this exploration are complementary rather than competing. Robots are better at surviving harsh environments and conducting repetitive measurements. Humans are better at geological sampling, improvised problem solving, and the kind of contextual judgment that makes the difference between a merely good sample and a scientifically transformative one. The fully developed interplanetary civilization that the Artemis program is beginning to build will be, in its most fundamental character, a scientific civilization, one whose relationship to the cosmos is defined by curiosity and investigation rather than resource extraction or territorial expansion. The children alive on Earth tonight, the generation that will be in their 20s and 30s when the first humans land on Mars, that will be in their 50s and 60s when the first permanent Mars settlement is established, that will live to see whether the search for life in the Jezero Delta samples returns a positive result or a negative one, will live in a world that is already different from the one we inhabit, in ways that the expansion into space will have shaped. They will grow up knowing that humans have walked on the moon again, that the first woman has left her footprints in the lunar regolith, that the first crew is on their way to Mars or has already arrived. The psychological and cultural effect of knowing that your species has done these things, that the boundary between humanity's home world and everywhere else is crossable, that the story of human civilization is larger than any single planet, is not quantifiable, but it is real. Every generation defines itself in part by what it believes is possible. The generation that inherits the early interplanetary era will believe, because it will know from direct evidence, that the next world is reachable. And the generation after that will believe the same about the world after that. The trajectory, once established, does not point back. Tonight, as you drift towards sleep on the single world we currently inhabit, the moon is rising somewhere above the horizon, its gray surface as patient and unchanged as it has always been. The rovers on Mars are trundling across their ancient valley floors, their instruments humming, their cameras recording. The engineers in their offices and laboratories are solving the next problem on the long list of problems between here and Mars. The astronauts in their training facilities are preparing their minds and bodies for the environments they will one day encounter. The scientists studying the samples and the telemetry in the orbital imagery are building, incrementally, the understanding of other worlds that will make it possible for humans to live there. And somewhere in all of that work, in all of those people, in all of those hours of careful and patient effort, the next chapter of the human story is being written. We are going back to the moon. We are going to Mars. Not because it is easy, it is not easy, and anyone who tells you otherwise is simplifying. But because the kind of species we are does not stop at the edge of the known, and the universe has left the next world close enough that we can reach it, and we are finally, again, after the long pause, reaching. The first steps are being taken right now. The first habitats are being designed. The first people who will land on Mars are, most likely, alive somewhere on Earth tonight, perhaps already selected in training, perhaps still children, perhaps not yet born. They are real. The world they will stand on is real. The distance between here and there is real and crossable. And the story that will be told about this era, of the return to the moon and the first footprint on Mars, will be one of the great chapters in the long and improbable history of a species that refused, generation after generation, to stop looking up. Good night. The next world is waiting.